If the chronicle of the cosmos' genesis, arguably the most compelling narrative ever conceived, fails to hold true, then what? The James Webb Space Telescope, humanity's most potent instrument for probing the vastness of space, was not conceived solely for aesthetic visual capture. Its fundamental purpose was to validate our preconceived notions regarding the Big Bang, the nature of time, and the inception of all existence. However, the revelations it has brought forth have profoundly reshaped our perception of the universe. We are observing galaxies that defy expectations, stars coalescing with improbable rapidity, and formations exhibiting a smoothness that challenges comprehension. All of this prompts the consideration that our prevailing origin story might be fundamentally flawed. This isn't merely a scientific adjustment. It carries the potential to redefine our understanding of reality itself. A telescope that has altered everything. For extended periods, researchers have directed their gaze ever deeper into the cosmos, yearning to witness the universe's inaugural light, a faint echo from the very beginning of time. The Big Bang Theory, for a considerable duration the predominant cosmological explanation, posited that the universe originated approximately 13.8 billion years ago, rapidly expanding from an infinitely dense state known as a singularity. From that foundational moment, all subsequent phenomena, stars, galaxies, and indeed ourselves, have been part of this outward trajectory. Images captured by Hubble and other observatories provided insights into the universe's expansion and corroborated many of our established understandings. Then, the James Webb Space Telescope emerged. The James Webb Space Telescope, or JWST, was engineered not for minor refinements, but to penetrate deeper into cosmic history than any predecessor. Its mission was to capture the luminescence of the earliest galaxies, and to bear witness to the cosmic dawn, the epoch when the first stars illuminated the primordial darkness. The culmination of decades of development, with an expenditure approaching $10 billion, it represents the most sophisticated space observatory ever constructed. Deployed in December of 2021, the Webb was anticipated to inaugurate a new era of cosmic comprehension. Few, however, foresaw that it might instead necessitate the revision of a narrative we believed to be settled. Upon the release of Webb's initial images, experts immediately recognized their divergence from expectations. While undoubtedly visually stunning, behind the resplendent glow of nascent galaxies and distant stellar bodies lay enigmas, incongruities, and structures of startling maturity. These formations did not align with the depiction of chaotic, nascent galaxies posited by Big Bang models. They were too substantial, too uniformly structured, and at times, seemingly too ancient. From an external perspective, they appeared conspicuously out of place. What most astonished observers was not simply the presence of these celestial bodies, but the temporal context in which they were observed. Current cosmological models suggest that hundreds of millions of years would be required following the Big Bang for the initial galaxies to coalesce. Yet, Webb has identified fully formed galaxies existing merely 200 to 300 million years after that presumed point of origin. Furthermore, these galaxies were not diminutive. In accordance with prevailing evolutionary theories, their considerable size, dynamism, and abundance of stars and heavy elements at such an early stage were unexpected. As further data became available, a discernible pattern emerged, an overabundance of galaxies, appearing too early, too massive, and too organized. This presented not a matter of recalibrating a few parameters or appending a minor footnote to existing theories, but a discrepancy of such magnitude that it threatened the fundamental tenets of our entire cosmological framework. One astrophysicist bluntly stated, "These galaxies shouldn't exist." Another likened the findings to encountering a classroom filled with adults when toddlers were expected. These were not the hallmarks of a young, turbulent universe just beginning to take shape, but rather indications of a universe that appeared mature from its inception. This leads to the profound question, what have we overlooked? Could our interpretation of redshift, the phenomenon of light stretching that indicates celestial distance, be inaccurate? Could cosmic time itself be playing a trick on us? Or is the very premise of a universe originating from a singular event inherently incorrect? The implications are immense. Some of the data from the James Webb Telescope consistently reveal early structural complexity where none should logically exist. This could pose a significant challenge to the Big Bang theory, potentially necessitating not just minor modifications, but a complete overhaul. This does not imply the absence of a cosmic beginning, but it strongly suggests that its nature may be vastly different from our current understanding, impacting our comprehension of its temporal progression, its spatial extent, or its underlying causal factors. Some scientists are now tentatively exploring the unthinkable. Perhaps the Big Bang was not the absolute beginning. Perhaps the universe has always existed, or it operates within a cyclical pattern of expansion, contraction, and rebirth, concepts we are only beginning to grasp. Undoubtedly, the James Webb Telescope has already instigated a paradigm shift. Its impact stems not from disproving the Big Bang theory, but from providing unexpected observations, the very hallmark of groundbreaking scientific inquiry. Ultimately, only one outcome prevails when opinion confronts empirical evidence. The universe operates according to its own laws, irrespective of our theories. Now, with the James Webb Telescope's observations, we can perceive it with unprecedented clarity. The James Webb Space Telescope was not merely an incremental upgrade to Hubble. It is a fundamentally distinct instrument engineered to address questions beyond Hubble's reach. While Hubble focused on visible and ultraviolet light, the James Webb is designed to observe in the infrared spectrum, a crucial wavelength for studying the early universe. The explanation is both simple and profound. As the universe expands, the light from ancient galaxies undergoes redshift, stretching into longer, fainter wavelengths. To comprehend the genesis of galaxies, stars, and cosmic structures, one must examine the extended, cooling afterglow of the past. This is precisely what the Webb telescope provides. Orbiting nearly 1 million miles from Earth at the second Sun-Earth Lagrange point, the Webb resides in Earth's shadow, shielded from solar radiation by a 5-layered sunshield the size of a tennis court. Operating in near absolute darkness, it can detect faint infrared signals that have traversed over 13 billion years of cosmic history. It is, by design, a time machine, not metaphorically, but literally. The farther the Webb looks, the older the light it captures. However, its design was not solely for distant observation, but for pioneering observation. A primary objective was to detect the very first stars and galaxies, a period in cosmic history known as the Cosmic Dawn. This era follows the so-called Dark Ages, a time after the Big Bang when matter had cooled sufficiently for atoms to form, but before stars had ignited. Scientists anticipated that Webb would identify the initial flickers of starlight that eventually illuminated the universe, marking the transition from cold, dark hydrogen clouds to luminous structures. The expectation was to witness galaxies forming in chaotic agglomerations, their stars composed primarily of hydrogen and helium with minimal metallic content. Essentially, the Webb was conceived to corroborate and refine our understanding of the Big Bang's aftermath by offering unparalleled detail of the universe's earliest light. It was also intended to answer other enduring questions. How do galaxies evolve? How do stars form within nebulae of gas and dust? Can we detect atmospheres around exoplanets? The Webb's massive 6.5-meter, gold-coated mirror, more than 2.5 times the diameter of Hubble's, was engineered to resolve these profound mysteries. It possesses the capacity not only to detect dim, distant objects, but also to reveal intricate structures and details with a precision previously unattainable. The scientific mandate was exceedingly broad. Researchers believed that by observing deep into space, they would witness the primordial chaos predicted by the Big Bang model, nascent galaxies in their initial stages of formation, exhibiting simple structures and irregular forms. Their hope was to observe the gradual development of complexity over eons, supporting a timeline where stars slowly synthesized heavier elements and galaxies coalesced through mergers, with structures evolving over billions of years. However, this is not what they observed. The initial images transmitted by the Webb were lauded for their beauty. Yet, it was the accompanying data that sent shockwaves through the scientific community. Instead of chaotic infant galaxies, the Webb revealed massive, well-defined systems astonishingly close to the supposed beginning of time. Rather than early, metal-poor stars, it detected objects rich in heavier elements that theoretically should not have existed so early. Instead of observing galaxies slowly assembling from cosmic dust, we were presented with snapshots of what appeared to be fully developed, mature structures coexisting when the universe was but a cosmic infant. This was not an issue of precision or interpretation. The observations directly contradicted what the Webb was expected to confirm. It performed all its intended functions. It peered to the edge of the observable universe, captured the faintest infrared light, and resolved galaxies never before seen. In doing so, however, it unveiled a startling truth. Our theories were unprepared. We constructed the most advanced telescope in history to validate our most cherished cosmological models, and it may instead be in the process of dismantling them. Every capability designed to reinforce our understanding of the Big Bang now seemed to cast new doubt. The timeline of cosmic evolution appeared compressed, and structures more developed. The formation of galaxies and stars, once believed to span hundreds of millions of years, now seemed to occur almost instantaneously. Adding to the perplexity, the Webb was functioning precisely as intended. There were no discernible malfunctions in its systems or calibration. Its sensors, such as NIRCam and NIRIS, delivered clear, comprehensive views. Its mirrors were perfectly aligned. The issue was not with the instruments, but with the underlying theoretical framework. The James Webb Telescope was not merely observing space. It was scrutinizing our fundamental assumptions. And the light it returned carried the unsettling implication that we might be mistaken, not about the data itself, but about its meaning. What the Big Bang Theory truly signifies requires a deeper understanding of what it challenges. The term, Big Bang, is so frequently and broadly applied, in documentaries, popular culture, and educational settings, that its precise scientific meaning is often obscured by oversimplification. The common conception portrays it as a singular, cataclysmic explosion that hurled matter into space. This is not entirely accurate. The Big Bang was not an event occurring within space. It was the explosive expansion of space itself. The Big Bang Theory is a mathematical model describing the universe's expansion. It posits that approximately 13.8 billion years ago, all of space, time, matter, and energy were concentrated in an unimaginably hot, dense state. This was not a point within space, but space itself compressed to a volume near zero. Subsequently, space began to expand, not into anything external, but as a stretching of the very fabric of reality. This expansion continues today, with galaxies not moving through space, but being carried apart by the increasing expanse of space between them. Substantial evidence supports this model. In 1929, astronomer Edwin Hubble provided a pivotal observation. Light from distant galaxies exhibited redshift, indicating it had been stretched to longer wavelengths. This implied these galaxies were receding from us, and the universe was expanding. This observation allows us to extrapolate backward to a time when the universe was smaller, denser, and hotter, ultimately leading to a singularity. In mathematical terms, this is the essence of the Big Bang Theory. Over the subsequent decades, further data bolstered this concept. In 1964, scientists accidentally discovered the cosmic microwave background radiation, or CMBR. The CMBR is a faint glow of microwave light emanating from all directions in space, interpreted as the residual cooled radiation from the hot, dense early universe, a phenomenon predicted by Big Bang proponents years earlier. Additionally, measurements of hydrogen, helium, lithium, and other light elements yielded abundances consistent with nuclear fusion occurring in the nascent, rapidly expanding universe. These findings coalesced into a remarkably successful framework. A universe born in intense heat, continuously expanding, cooling, and gradually forming stars, galaxies, and ultimately life. The model proved so effective that it became standard cosmology, integrated into textbooks, simulations, and global scientific consensus. However, despite its success, certain anomalies persisted. The horizon problem questioned why widely separated regions of the universe exhibit such remarkable uniformity when they should not have had sufficient time to exchange information or energy. The flatness problem sought to explain why the universe's geometry appears so close to being perfectly flat. The monopole problem questioned the absence of expected high-energy particles, which should have been present if the universe originated as theorized. To address these issues, cosmologists introduced a concept in the 1980s called cosmic inflation. This theory proposed that in the first infinitesimal fraction of a second after the Big Bang, the universe underwent an exponential expansion exceeding the speed of light. This inflationary period would have smoothed out initial irregularities, flattened the universe's geometry, and diluted hypothetical exotic relics. Inflation became an adjunct to the standard model, not an original component of the Big Bang theory itself, but now intrinsically linked to most contemporary versions. Consequently, when scientists refer to the Big Bang today, they typically mean a composite theory, an initial singularity followed by rapid inflation, then slower expansion, cooling, the formation of hydrogen and helium, the emission of the CMBR, and finally, the emergence of structure. It is crucial to note that the Big Bang theory does not attempt to explain the ultimate cause of the universe's beginning or what preceded it. In fact, within the conventional framework, time itself commenced with the Big Bang. There is no before. The theory also offers limited insight into the true nature of the singularity, as our current equations break down under such extreme conditions, where quantum effects dominate and general relativity loses its predictive power. This is precisely where the findings from the James Webb Telescope become so disquieting. The theory predicts a slow, gradual development of structure from an initial state of chaos. Galaxies should form incrementally over vast timescales. Stars should evolve through established nuclear fusion processes, and all these phenomena should align with the timeline established by cosmic microwave background and redshift measurements. However, if the Webb is observing galaxies that are too ancient, too massive, and too organized at such early epochs, then that established timeline may be erroneous. And if the timeline is incorrect, then the foundational principles upon which redshift, distance, and age are calculated might also be flawed. This could imply that the universe's age, or even its rate of expansion, is inaccurately determined. More critically, our understanding of space, time, and light may be incomplete, rendering our entire cosmological model precarious. Anomalous galaxies in Hubble's deep field. Astronomers had long suspected discrepancies in galactic evolution even before the James Webb Space Telescope delivered its astonishing images. The Hubble Deep Field, one of the most iconic photographic collections ever produced, offered the initial hints. What began as a daring gamble for telescope observation time evolved into a revolutionary method of peering into the past. In 1995, astronomers directed the Hubble Space Telescope towards a region of the sky that appeared utterly devoid of celestial objects. No stars, no galaxies, no discernible targets, only darkness. The telescope shutter remained open for 10 consecutive days. The revelation that followed stunned the scientific world. thousands of galaxies densely packed into what seemed like empty space. Each faint smudge, each spiral or nebulous arc represented a galaxy, some situated over 10 billion light-years away, meaning we were observing them as they existed near the dawn of time. This single image revolutionized astronomy, demonstrating that the universe contained far more galaxies than previously estimated. It validated the concept that by observing deeper into space, one could witness progressively earlier stages of the universe's evolution. Over subsequent years, Hubble employed this technique repeatedly, creating the ultra-deep field and the extreme deep field, images that pushed the observational limits closer and closer to the theoretical threshold of visibility. However, as resolution improved and redshift data accumulated, a curious pattern began to emerge. Certain galaxies within these deep field images appeared too developed for their inferred age. They exhibited complex structures, including spiral arms, central bulges, and even signs of rotation. These were not the disordered, rudimentary proto-galaxies expected from simulations of the early universe. They appeared as mature galaxies. Yet, according to redshift calculations, they existed merely a few 100 million years after the Big Bang. Initially, these anomalies were dismissed as isolated instances. It was possible that the galaxies were misidentified, their light distorted by gravitational lensing, or that it was simply a statistical fluke, a few unusual cases that did not fundamentally challenge the prevailing model. Nevertheless, a sense of unease persisted. Numerous studies emerged, all pointing to the same conclusion. Galaxies appeared too early, stars possessed unexpected metallic compositions, and black holes were disproportionately massive for their age. While the fundamental model remained the most viable, it was experiencing significant challenges. The core issue revolved around cosmic timelines. According to the Big Bang framework, it should require hundreds of millions of years for gravity to gather gas into stars, for those stars to undergo their life cycles and demise, and for their remnants to form more complex systems. Heavy elements, which astronomers refer to as metals, are synthesized within stellar cores and dispersed by supernovae. Therefore, the early universe should have been characterized by a low metal content and primitive structural organization. Yet, some galaxies observed in the Hubble Deep Field defied this expectation, appearing chemically enriched, tightly bound, and rotationally stable. The case of the galaxy designated GNZ11 is among the most compelling. Hubble initially identified GNZ11, and subsequent spectroscopic analysis confirmed its existence. It appeared to be present only 400 million years after the Big Bang. However, its mass was equivalent to that of a billion suns, and it displayed signs of star formation at a rate considered impossible at that epoch. Not only was it persisting, but it was actively growing. Despite these findings, astronomers remained cautious. While Hubble's capabilities were groundbreaking, they had inherent limitations. The deeper it observed, the more challenging it became to distinguish faint galaxies from background noise. Furthermore, infrared sensitivity, crucial for detecting highly redshifted objects from vast distances, was not Hubble's forte. What was clearly needed was a telescope capable of observing deeper with greater precision, and with an instrument tuned to the faint, stretched light of the early universe. That instrument would be the James Webb. Crucially, it is important to understand that Webb's most startling discoveries did not arise in a vacuum. The groundwork for the current cosmological quandary was already laid in the deep field images. Indications were present of galaxies evolving too rapidly, stars forming in unexpected environments, and mass accretion occurring at a pace that defied current models. The manner in which science addresses such contradictions is what makes this potential paradigm shift so significant. Initially, such anomalous data is often disbelieved, then subjected to rigorous scrutiny, questioning, and frequently integrated into existing theoretical frameworks. However, at a certain point, when anomalies accumulate and can no longer be readily explained away, science is compelled to adapt. What began as a few unusual galaxies in a deep field image may now be recognized as the initial fissures in the foundation of the Big Bang Theory. An excessive number of mature galaxies appearing too soon. Not only did the James Webb Space Telescope capture breathtaking images of the cosmos, but it also revealed a profound challenge to our understanding of cosmic chronology. It was believed that gravity and atomic processes would gradually assemble galaxies over billions of years. However, these galaxies were discovered to be fully formed, substantial, organized, and remarkably ancient, existing mere hundreds of millions of years after the so-called Big Bang. The issue was not isolated. There were simply too many such instances. Within weeks of the James Webb Space Telescope's initial deep-field observations being disseminated, the astronomical community began to observe a phenomenon entirely contrary to their expectations. A population of galaxies so immense and mature that they defied current cosmological models. Scientists had anticipated encountering nascent, amorphous gas clouds, mere proto-galaxies in the nascent stages of formation. Instead, they were confronted with colossal systems, some possessing stellar masses equivalent to our own Milky Way, flourishing a mere 300 to 400 million years after the presumed inception of the universe. According to the prevailing standard cosmology, this scenario is deemed impossible. The universe requires time for atoms to coalesce following the Big Bang. Subsequently, gas clouds necessitate a considerable period to collapse into stars, and an even longer duration for those stars to exhaust their fuel, disseminate heavier elements, and give rise to subsequent stellar generations. Galaxies are not expected to appear fully formed at the dawn of time. Rather, they are theorized to grow incrementally over billions of years, shaped by mergers, intense bursts of star formation, and complex feedback mechanisms. However, Webb's revelations depict a cosmos resembling an elaborate exhibition, meticulously assembled and polished far earlier than theoretical frameworks permit. A team of researchers, spearheaded by Dr. J. Giancartali, conducted one of the pioneering analyses that ignited considerable concern. Examining early scientific data from the James Webb Space Telescope, they identified dozens of exceptionally luminous and massive galaxies exhibiting redshifts exceeding 10. For such a cosmic epoch, this corresponds to a universe younger than 500 million years. Astonishingly, these galaxies displayed characteristics not only of substantial size, but also of chemical richness and well-defined structural morphology, exhibiting shapes like rings, bulges, and even spiraling arms. They appeared less like nascent entities, and more like venerable survivors from a distant past. This discovery was not merely surprising, it was, by the mathematical underpinnings of the Big Bang model, inexplicable. The creation of galaxies of such magnitude would necessitate either star formation occurring at an unprecedentedly rapid rate, the operation of unknown mass accumulation mechanisms, or a fundamentally different chronological sequence for the early universe. The quantitative data simply did not align. The rate at which matter could aggregate, form stars, and organize into galactic structures was demonstrably insufficient to account for the sheer volume of galaxies Webb was detecting, not at that speed. Some endeavors were made to reconcile these findings by adjusting star formation models, positing that these early galaxies were forming stars with far greater efficiency than previously imagined. However, this hypothesis encountered its own limitations. The more efficient stars form, the greater the radiation and feedback they expel, which should theoretically inhibit, rather than accelerate, further star formation. Others proposed the possibility of misidentification of these galaxies or inaccuracies in redshift estimations. Yet, subsequent spectroscopic confirmations provided robust validation, affirming that these galaxies were indeed as ancient and massive as they appeared. The sheer abundance of fully developed galaxies compelled cosmologists to pay serious attention. While one or two anomalies might be dismissed, Webb's research indicated a discernible trend, a statistical reality that could not be ignored. The early universe not only appeared more organized than anticipated, but also contained a significant number of large structures. This raised a fundamental question: was our comprehension of cosmic time itself flawed? If galaxies were forming at such an accelerated pace, perhaps temporal progression in the early universe operates differently than currently understood. Alternatively, it's conceivable that redshift does not correlate linearly with distance and age, at least not according to our current models. If this were the case, a foundational element of observational cosmology, our method for ascertaining the age of distant celestial objects, might require fundamental reevaluation. The implications for our understanding of cosmic development become even more profound when considering the consequences. What would this signify for our knowledge of structure formation, dark matter dynamics, and feedback processes if galaxies did not require billions of years for complete development? It's akin to discovering skyscrapers within fossils from the Bronze Age, indicating a significant disruption in the expected order of events. For decades, the Big Bang Theory has transcended its role as a mere scientific model, serving as a creation narrative articulated through equations and light, charting a course from simplicity to complexity, from hot plasma to the emergence of humanity. However, Webb's observations have cast doubt upon the temporal pacing of this grand narrative. Perhaps the script itself is not erroneous, but its timing is. Or, more radically, the story we have been recounting is either incomplete or entirely inaccurate. And this is merely the nascent stage of discovery. Over the coming years, the James Webb Space Telescope will conduct more detailed observations of these early galaxies, employing enhanced spectroscopy, refined imaging, and deeper surveys. These investigations will either corroborate these anomalies or reveal their proliferation. Regardless, the scientific tension is escalating. Galaxies that are too large, too old, and too rapid in their formation. Astronomers had anticipated that the initial deep-field images from the James Webb Space Telescope would reveal small, disorganized galaxies, essentially preliminary sketches that would eventually mature into elegant spiral and massive elliptical galaxies. Instead, they encountered objects that should not have been present, galaxies that appeared fully realized, substantial, ancient, and rapidly developing. These were not isolated anomalies or mere errors. They were pervasive across Webb's field of view, directly contradicting the conventional narrative of universal evolution. Our current cosmological framework posits a specific rate of formation for cosmic structures. Galaxies are theorized to commence as small aggregations of matter in the nascent universe, gradually expanding over eons through mergers, gravitational accretion, and episodes of intense star birth. This hierarchical model, wherein smaller structures coalesce into larger ones, is intrinsically integrated into Big Bang cosmology. Yet, Webb has identified galaxies that seem to bypass this entire developmental phase, appearing massive and intricate at an exceedingly early cosmic juncture. One particular galaxy, designated as Source 1019, is estimated to have existed as early as 500 to 600 million years after the Big Bang. Astonishingly, its mass appears to rival that of the Milky Way, a system that required over 13 billion years to achieve its current form. How could such a colossal structure already exist when, according to established models, there simply hadn't been sufficient time for such extensive development? The data indicated that these galaxies were not merely visible, but actively thriving. Some were generating stars at rates 10 to 20 times greater than predicted. Others exhibited signs of organized rotation, featuring distinct galactic disks, a characteristic that typically necessitates substantial time, mass, and stability for development. It was not solely their size that raised questions. it was also their perceived age, or at least the implications for the passage of time in the early universe. If they were indeed fully formed at such high redshifts, it implied that their constituent stars must have begun forming even earlier, potentially within the first 100 to 200 million years of cosmic history. This represents an exceptionally brief window for processes such as cooling, gas cloud collapse, star formation, and galactic organization, significantly shorter than what the Big Bang model typically accommodates. Another perplexing aspect pertains to their velocity, or the rate at which these galaxies were forming stars and accumulating mass. The observed star formation rates were frequently so high that they surpassed the Eddington limit, which defines the maximum rate at which matter can accrete onto a structure without being dispersed by radiation pressure. These galaxies were not only growing rapidly, but doing so at speeds that pushed the boundaries of astronomical possibility. The confluence of three factors, excessive size, extreme age, and accelerated development, created a profound contradiction. It is insufficient to merely offer a singular explanation for one unusual characteristic. To achieve numerical consistency, substantial modifications to the prevailing theory would be required, and even then, the underlying discrepancies would not fully dissipate. The Big Bang model's robustness is continually tested by each massive, early galaxy that Webb discovers. As a means of interpreting these findings, scientists have proposed that early galaxies might have possessed a greater efficiency than their modern counterparts, for instance, by consuming their gas reserves more rapidly. However, this merely postpones the fundamental problem. How could such a high degree of efficiency manifest so swiftly, in such vast numbers, and across such extensive regions of the early universe? Furthermore, why did prior models not predict this phenomenon? Another theoretical avenue suggests that the clumping of dark matter in the early universe may have created deep gravitational potential wells, facilitating matter accretion at a faster rate than expected. Yet, even this adjustment struggles to account for the sheer quantity of massive galaxies detected by Webb. Moreover, it does not explain the observed metallicity and organized structures present in so many of them. If the timeline of galaxy formation is inaccurate, it could imply that our distance measurements, largely reliant on redshift, necessitate re-examination. It might also suggest that time in the early universe operated under different principles than we currently assume, or that the model of cosmic expansion itself requires updating. It is even conceivable that the fundamental laws of physics, as observed today, did not apply with the same exactitude in the universe's infancy. These questions are now reverberating through astrophysics like seismic waves. The standard cosmological model, known as lambda-cold dark matter, LCDM, has long been regarded as exceptionally robust, accounting for cosmic expansion, the cosmic microwave background radiation, large-scale structures, and more. However, Webb's discoveries are now probing the very limits of that confidence. Some scientists have even characterized these early results as a crisis in cosmology, one that demands either substantial revision or radical reinterpretation. Meanwhile, the Webb telescope continues its relentless delivery of data. Each new image, each deeper exposure, appears to unveil yet another galaxy that is too large, too old, or too rapidly developing to conform to the established timeline. And while researchers are diligently working to refine measurements and test alternative hypotheses, the overarching picture is becoming increasingly difficult to disregard. The early universe appears far more akin to a bustling cosmic metropolis than a nascent construction zone. It remains premature to definitively state whether these discoveries will completely overturn the Big Bang theory. Paradigms do not collapse overnight. However, history demonstrates that when observational evidence contradicts theoretical predictions, the onus falls upon the theory to adapt. Redshift reconsidered. One of the most fundamental concepts in astronomy is redshift, which serves as our primary indicator of an object's distance and, consequently, its age in cosmic time. It is the very metric that allows us to determine how far away a galaxy is, and how far back in time we are observing it. However, the recent discoveries made by the James Webb Space Telescope have prompted some scientists to question the accuracy of our interpretation of redshift. To grasp the significance of this inquiry, it is essential to understand what redshift is fundamentally understood to represent. As light travels from a distant celestial body through the expanding fabric of space, its wavelength is stretched. Analogous to the lowering pitch of a receding ambulance's siren, the wavelength of light increases as its source moves away from the observer. This phenomenon causes blue light to shift towards the red end of the spectrum, hence the term redshift. In cosmology, redshift is also employed to track cosmic expansion. A higher redshift value indicates a greater distance to the object and, crucially, a deeper look into the past. An object with a redshift of 2, for instance, is being observed as it existed when the universe was approximately 3 billion years old. An object at redshift 10 signifies an observation from a time when the universe was less than 500 million years old. Consequently, a higher redshift value brings us closer to the Big Bang. We utilize this relationship to construct the entire cosmic timeline, from the formation of stars and galaxies to the appearance of black holes, and even the rate of universal expansion. In essence, redshift is not merely a measurement, it is the very backbone of cosmic history. The galaxies observed at extreme redshifts, values of 10, 11, 12, and beyond, are not behaving as anticipated. They are too large, too evolved, and too structured, as if they have had considerably more time to develop than the established timeline permits. One proposed explanation is that these galaxies are somehow younger than they appear, and their observed brightness, mass, or structure is misleading. However, a more radical possibility is that our interpretation of redshift itself is flawed. Could it be that redshift does not convey what we believe it does? Could cosmic expansion not be the sole, or even the correct, explanation for why light becomes stretched over vast cosmic distances? This is not a novel question. It represents one of the oldest controversies in cosmology. When Edwin Hubble first observed that galaxies were redshifted and appeared to be receding from us in the early 20th century, some scientists proposed alternative explanations. The tired light theory was one prominent hypothesis, suggesting that photons lose energy through interactions with particles or fields in space, thereby becoming redder. Under this theory, redshift would not indicate cosmic expansion, but rather the fatigue of photons after traversing immense distances. This theory eventually fell out of favor due to a lack of supporting evidence and its inability to accurately match certain observed cosmic features, such as the precise spectrum of the cosmic microwave background. Nevertheless, Webb's findings are breathing new life into these age-old debates. If expansion alone cannot adequately explain the unexpected maturity of high redshift galaxies, could something else be influencing our interpretation of redshift? On a more theoretical level, certain hypotheses question the nature of redshift itself. Some researchers posit that spacetime might not have been uniform, particularly in the early universe. Light may have undergone redshift in ways that are currently beyond our comprehension, perhaps influenced by greater curvature of spacetime or stronger quantum fluctuations in the past. Others suggest that light could interact with dark matter or dark energy in ways that alter its frequency over billions of years. Still others point to the possibility that light behaves differently at quantum scales, implying that redshift could be affected by factors entirely outside the purview of the standard model. If space is granular, if time is emergent, or if the speed of light has varied throughout cosmic history, then our entire understanding of redshift might be built upon an unstable foundation. There is also the disquieting realization that much of our redshift calibration relies on models that we are now actively questioning. We use redshift to estimate distance, but we also employ models of galaxy evolution to infer redshift. This circular reasoning becomes problematic when the very models used to interpret redshift are being challenged by the data from Webb. It is, of course, too early to completely discard the concept of redshift. It remains one of the most predictive and consistent features of cosmology. However, the precision with which we equate redshift to time and distance may indeed require recalibration. It is possible that redshift does indicate expansion, but not in a uniform, one-size-fits-all manner, or that in the earliest epochs, an unknown factor distorted the relationship we have come to trust. The impossible stars. The first generation of stars, known as population 3 stars, were anticipated to be among the earliest objects observable by the James Webb Space Telescope. These stars are theorized to be massive, extremely hot, and composed primarily of hydrogen and helium, representing the initial sources of light in the universe. They were expected to have formed in an environment devoid of heavy elements. Instead of finding these long hypothesized primordial stars, Webb has detected something vastly different. Stars that should not exist at such an early cosmic epoch and whose formation appears inconsistent with the standard cosmological model's timeline and chemical composition. Webb has observed massive, luminous stars embedded within ancient galaxies, radiating intensely not only with hydrogen and helium, but also exhibiting clear signs of metallicity. In astrophysical terms, metals encompass any element heavier than helium, including carbon, oxygen, nitrogen, and iron, all of which are synthesized within the cores of stars and subsequently dispersed through supernova explosions. The presence of these heavier elements in early stars implies that multiple generations of stellar birth and death must have already occurred. Yet, Webb is observing these chemically enriched stars a mere few 100 million years after the presumed Big Bang. This leaves an astonishingly brief period for multiple stellar generations to live, die, and recycle their constituent materials into subsequent, more complex offspring. This scenario is astrophysically implausible. Within the framework of the Big Bang, the first stars are predicted to form after cosmic recombination, when electrons and protons combine to form neutral atoms, and the universe cooled sufficiently for gas to collapse under gravitational influence. These population 3 stars, if they existed, were expected to have had short, energetic lifespans, culminating in brilliant supernovae that would seed the universe with heavier elements, paving the way for second and third generation stars. However, this process requires hundreds of millions of years, if not longer, to accumulate the levels of metallicity observed in stars that appear to exist far too early. Webb's discovery of stars with high metallicity at such extreme redshifts presents a significant challenge. It suggests not only early star formation, but also early chemical evolution occurring at a speed and scale that current models cannot replicate. In galaxies such as GZ11 and Source 1019, stars appear to be not only intensely hot, but also chemically complex. This complexity necessitates a stellar life cycle that should be impossible within such a compressed cosmic timescale. Some experts have attempted to address this by proposing that stars formed exceptionally rapidly in the early universe. It is conceivable that the conditions within the very first galaxies facilitated a much faster rate of star formation, lifespan, and death than previously understood. These early stars might have been denser, cooler, or experienced shockwave-induced collisions that immediately initiated the chemical cycle. However, this explanation faces a logical hurdle. Webb is not detecting a single enriched star or galaxy, but a substantial population of them. This widespread pattern suggests that the early universe was not a pristine, blank canvas awaiting artistic creation, but rather a scene already populated with intricate details. Even more perplexing are stars that appear too massive for existing theories to adequately explain. Based on Webb's observations, some of these stars may possess masses hundreds of times greater than our Sun, approaching theoretical upper limits. The conventional understanding is that such massive stars are inherently unstable, with radiation pressure either disintegrating them or causing them to collapse into black holes. Yet, within the early galaxies observed by Webb, these colossal stars not only appear to be possible, but seem to be commonplace. These seemingly impossible stars shine with such luminosity and complexity that it is difficult to envision their formation without some form of precursor conditions. However, there should not have been sufficient time since the universe's presumed origin for those conditions to arise. Even accounting for gravitational collapse and rapid cooling, the interval between the Big Bang and the formation of these stars is alarmingly short. What if the universe did not commence with simple hydrogen clouds and a pristine state? What if, instead, the early universe was already chemically active, already forging stars with metals, already assembling systems far more advanced than we anticipated? This would imply a vastly different origin, or at least a profoundly different temporal progression, than the Big Bang theory currently allows. Certain unconventional hypotheses, such as plasma cosmology or steady-state models, propose an endless or cyclical universe where matter and energy are in a perpetual state of transformation rather than originating from a singular event. These perspectives suggest that early stars are not truly early, but rather an integral part of a continuous, recurring process within the cosmos. While these models have largely fallen out of favor, Webb's findings are prompting renewed consideration. There is also the possibility that our entire model of stellar evolution is incomplete. Perhaps the physics governing the early universe permitted faster nuclear fusion, abbreviated lifespans, or exotic stellar behaviors that we have yet to identify. It is conceivable that dark matter played a catalytic role, or that an unknown factor influenced the processes of stellar birth, life, and death. However, until these knowledge gaps are addressed, we are left with a universe that appears to defy established rules. The stars that were presumed to be impossible, too massive, too old, too chemically enriched, are not only real but prevalent, and they are fundamentally rewriting the narrative of how light reemerged in the cosmos. Ancient black holes, where there should be none. Black holes are frequently conceptualized as the universe's grim reapers, representing the dense, collapsed remnants of exceptionally massive stars, or the colossal entities that reside at the centers of galaxies. Their formation is neither a simple nor a rapid process. Within our current cosmological framework, stellar remnants known as black holes are conventionally understood as representing the ultimate endpoint of cosmic evolution. Their existence, from formation through their entire life cycle, necessitates the development of successive generations of stars. They require the merging of significant masses and a protracted, gradual accretion process for their construction. However, the observations from the James Webb Space Telescope reveal their presence with surprising frequency and at an unexpectedly early stage of the universe's history, and indeed, at sizes far exceeding expectations. Supermassive black holes, those possessing masses equivalent to millions, or even billions, of our Sun, are typically associated with galaxies that have undergone extensive development. Our own Milky Way galaxy contains such an object, Sagittarius A*, serenely positioned at its core, acting as a gravitational linchpin that coalesced over billions of years. Yet, Webb's data is detecting active galactic nuclei, or AGNs, which are brilliant, energetic indicators of matter spiraling into black holes within galaxies that came into existence less than 700 million years following the Big Bang. Some of these black holes already appear to possess masses in the hundreds of millions of solar masses, and this timeline presents a significant challenge. This is not a phenomenon that can occur rapidly. It requires substantial time. Even if one were to begin with a nascent black hole, perhaps the remnant of a particularly massive population 3 star, estimated to be around 100 solar masses, It would need to continually grow through the absorption of surrounding matter and collisions with other galaxies to achieve supermassive status. Under even the most optimistic theoretical models, this process takes hundreds of millions to billions of years to complete. Conversely, Webb's observations show these entities as fully developed before the universe had reached its current maturity. This isn't merely early black hole formation. It signifies early black hole dominance. Some of the galaxies hosting these objects appear to be centered around these giants, suggesting that black holes were not merely a consequence of galactic formation, but perhaps a prerequisite. This perspective fundamentally challenges the traditional understanding. The galaxy known as Gigahertz 239a is one of the most striking examples. It is an active galaxy harboring a colossal black hole that was already present when the universe was approximately 570 million years old. Even more astonishing is the indication that it is actively accreting matter, meaning it was not dormant, but was vigorously consuming gas and altering its immediate environment. This is the type of behavior typically observed in galaxies that are far more advanced in their evolutionary journey. Some researchers have put forth the hypothesis that these black holes originated from direct collapse, an alternative formation pathway wherein massive gas clouds directly collapse to form a black hole without first going through a stellar phase. This mechanism would result in the creation of larger initial black holes, enabling them to grow more swiftly. However, even this theory struggles to account for the presence and active accretion of such massive seeds at such an early epoch, particularly within galaxies that are also exhibiting rapid star formation. To grow with such velocity, these nascent black holes would require not only substantial mass, but also an abundant source of fuel. This includes cold gas, dust, and matter falling into them at a precisely regulated rate. Yet, such steady and rapid accretion contradicts many of our prevailing models, which presuppose that turbulence, feedback mechanisms, and fragmentation would impede such a rapid growth process. Nevertheless, Webb is detecting these behemoths as already fully formed and active, quietly defying every timeline we had previously understood. Even more concerning is the sheer number of early supermassive black holes observed. They are not rare anomalies, but appear to be common constituents of early galaxies. This implies a universal formation process rather than an exceptional occurrence. Consequently, this suggests that our fundamental assumptions may be flawed. The existence of such massive black holes at such an early stage fundamentally alters our comprehension of structure formation, stellar evolution, and even the epoch of reionization, the period during which the universe transitioned from an opaque state to transparency under the influence of the first light sources. Black holes, through the energetic radiation they emit, may have played a significantly more profound role in shaping the nascent cosmos than was previously hypothesized. Some scientists are even beginning to propose that black holes might not represent the conclusion of cosmic evolution, but rather its inception. Certain models now posit that primordial black holes, which did not form from stars, but from quantum fluctuations in the extremely early universe, might have been the very first entities to initiate galaxy formation. In this revised narrative, black holes did not await the formation of galaxies around them. Rather, galaxies coalesced around these pre-existing black holes. This is a disconcerting paradigm shift, compelling cosmologists to grapple with potentially unsettling possibilities. If supermassive black holes are indeed this ancient, this prevalent, and this central to galactic existence, then perhaps our universe did not unfold in the slow, linear progression we had envisioned. It might have rapidly developed into complexity far sooner than we had previously considered possible, or perhaps it possessed this complexity from its very inception. The integrity of dark matter has been a cornerstone of cosmological understanding for decades. This enigmatic substance, comprising over 80% of all matter in the universe, is credited with holding galaxies together. It is non-luminous, reflective, and does not engage with the electromagnetic force. However, its gravitational influence permeates the cosmos, a fact we had previously accepted. The James Webb Space Telescope has now entered the observational arena. Webb's scrutiny of the universe's most ancient galaxies and structures has not only prompted questions regarding their age and size, but has also begun to challenge the very framework designed to contain them. Specifically, when we apply dark matter models to Webb's data, a deeply troubling discrepancy emerges. The mathematical relationships do not align. The standard cosmological model, known as lambda-CDM, posits that dark matter coalesced early in the universe, creating gravitational potential wells that attracted ordinary matter. This clumping is presumed to have initiated the formation of galaxies, stars, and subsequently planets. Dark matter was not merely a passive observer, but the primary architect of cosmic structure. However, Webb's observations now indicate that large, well-defined galaxies appeared far earlier than the lambda-CDM model permits. If these galaxies possess dark matter halos, as the model dictates, then these halos would have needed to form with extraordinary rapidity, exceeding the rate allowed by the model. In essence, if dark matter was operative in the early universe, it was functioning far too swiftly. Alternatively, Webb's observations of certain galaxies suggest they rely less on dark matter than previously assumed. The spectral data used to determine their mass distributions and rotational characteristics do not consistently align with expectations derived from dark matter. These galaxies behave as though they are bound by less unseen matter than the model predicts. This is not the first instance where dark matter has been a subject of scrutiny. Even within the relatively nearby universe, certain galaxies, such as NGC 5236, have appeared to contain virtually no dark matter, defying established galactic formation theories. However, these were isolated anomalies. Webb's findings indicate that the earliest galaxies, presumed to be entirely shaped by dark matter, are not exhibiting the expected behavior of dark matter-dominated systems. The distribution of cosmic structure also presents a point of tension. According to lambda-CDM, dark matter requires time to aggregate into clumps. Initially, the universe should have been largely uniform, with minor fluctuations gradually evolving into filaments, nodes, and voids. Yet, Webb is discovering galaxies that are not only more densely packed and aligned but, at times, more orderly than theoretical predictions suggest. Without substantial dark matter scaffolding, such a degree of order should not be present. The question then arises, from whence did this order originate? If dark matter lacked the necessary time to establish itself in such configurations, several possibilities arise. Firstly, dark matter might behave differently than we currently understand. Perhaps it is not as cold as lambda-CDM implies. If it were warm or self-interacting, it could clump more rapidly or distribute itself in an alternative manner. However, these modified dark matter theories introduce their own challenges and do not fully reconcile with other observations, such as those of the cosmic microwave background or galactic cluster dynamics. Secondly, it may indicate that alternative gravity theories, long relegated to speculative status, warrant re-examination. Models such as MOND, modified Newtonian dynamics, or TEVIS, tensor vector scalar gravity, attempt to explain galactic rotation and structure without invoking dark matter, by proposing modifications to the laws of gravity on large scales. These theories have faced difficulties in accounting for all observed phenomena, particularly on cosmological scales. However, Webb's revelations might provide new impetus for hybrid models that integrate modified gravity with a diminished role for dark matter. Thirdly, and perhaps most profoundly, it could signify that dark matter, as we conceive of it, simply does not exist, or at least not in the form we have theorized for nearly half a century. Our gravitational equations might be incomplete. Our understanding of mass and energy within curved spacetime may be flawed, or we might be overlooking a fundamental aspect of physics, one that Webb is beginning to unveil, not through direct observation, but through persistent discrepancies between theoretical predictions and observed reality. The profound significance of this issue lies in the fact that dark matter is not merely a hypothetical placeholder in our models. Contemporary astronomy, astrophysics, and particle physics are fundamentally constructed upon its premise. In many respects, it provides the explanatory power for how galaxies form and how the universe is structured. Dark matter is essential for the subsequent chain of cosmic events. If it fails, the entire edifice crumbles. James Webb does not directly detect dark matter. It is incapable of doing so. However, by pushing the boundaries of observational limits in terms of time and resolution, it is probing the consequences of dark matter's hypothetical existence. And these consequences are increasingly appearing strained. Reconsidering cosmic inflation. For an extended period, cosmic inflation has been regarded as one of the most robust explanations for the universe's characteristics. It was a significant augmentation to the Big Bang theory when initially proposed in the early 1980s. It was not an intrinsic component of the original framework, but was introduced to address several of its most significant shortcomings. The central tenet of inflation is that the universe underwent an extremely rapid, exponential expansion in the briefest fractions of a second after the Big Bang. Space expanded at a rate exceeding the speed of light for a transient but critical interval, rendering the universe flat, uniform, and even. Inflation was conceived to resolve specific cosmological puzzles. The horizon problem, for instance, questions why the universe appears uniform in all directions, despite distant regions seemingly lacking sufficient time to have exchanged light or information. Inflation proposes that these regions were once in close proximity before the inflationary expansion propelled them apart. Then, there is the flatness problem. The universe exhibits a geometrically flat structure, a state that should statistically be exceedingly improbable. Inflation suggests that this outcome arises when a small, curved region of space is expanded. Its curvature is effectively flattened. This explanation is both elegant and mathematically sound. However, there is a critical aspect. Inflation, in its initial formulation, did not yield direct, testable predictions. It was speculative and, for many years, remained on precarious theoretical footing. Subsequent refinements introduced greater mathematical rigor, and its predictions, particularly concerning the spectrum of cosmic microwave background fluctuations, aligned remarkably well with observational data, solidifying inflation's position within mainstream cosmology. It became standard cosmological doctrine. Nonetheless, inflation has consistently carried an aura of speculative ingenuity, a solution layered upon previous workarounds. With the advent of early data from the James Webb Space Telescope, the very questions that inflation was designed to resolve are re-emerging. Webb is not directly observing the inflationary epoch itself, which would have occurred approximately 10 to the power of -36 seconds after the Big Bang, a time so primordial that not even light had yet come into existence. However, Webb is examining the large-scale structure of the early universe, which is a direct consequence of that inflationary period. We observe that the cosmic structure appears exceptionally well organized, remarkably perfect, and at times, surprisingly ancient, the more we observe. The galaxies that Webb is detecting are not merely forming earlier than anticipated. They seem to appear fully assembled, possessing substantial masses and ordered rotational patterns, as if they bypassed any chaotic evolutionary stages. This presents a significant problem, because inflation was intended to explain the emergence of structure by introducing minute quantum fluctuations into an initially uniform universe. These fluctuations were meant to serve as seeds for the subsequent growth of galaxies, stars, and cosmic clusters. But what occurs when this structure materializes almost instantaneously, without sufficient time for fluctuations to evolve? The paradox is inverted. Inflation was designed to introduce a precisely calibrated degree of irregularity into a fundamentally smooth universe. However, Webb's observations of early galaxies suggest they have bypassed this irregularity altogether. They imply a universe that transitioned directly from inflation, or a similar process, into a state of complexity. This implies either that inflation operated in a manner vastly different from our current understanding, or that it did not occur at all. Inflation predicts a very specific distribution of fluctuations, with certain scales of structure being more prevalent than others. Yet, the cosmic web, even in its early stages, appears to exhibit a puzzling uniformity, one that does not align neatly with the predictions derived from inflationary theory. If this trend persists, it could signal a more fundamental inconsistency between inflationary predictions and the observed evolution of the universe. Beyond these empirical challenges, there are also philosophical concerns. While inflation offers mathematical utility, it carries unsettling implications. It frequently leads to the concept of a multiverse, suggesting that inflation did not occur just once, but continues indefinitely in various regions, thereby creating an infinite number of distinct universes. By definition, these universes are unobservable, rendering the theory exceedingly difficult to falsify and placing it perilously close to philosophical speculation, a characteristic generally considered undesirable in scientific theory. Webb's findings compel us to reconsider a crucial question: did the universe truly require a brief period of unimaginable expansion to account for its current state? Or have we been employing inflation as a means to paper over deficiencies in a model that was never as coherent as we believed? Some researchers are revisiting older concepts, such as bouncing or cyclic cosmologies, wherein the universe did not originate from a singularity but from the collapse of a preceding universe. Others are exploring quantum gravity frameworks where space and time are emergent properties, and the necessity for inflation evaporates entirely. The problem of the excessively smooth universe. The early universe is commonly envisioned as a realm of high-energy particles, intense turbulence, and profound chaos. The expectation was that the universe would gradually transition from this tumultuous beginning, giving rise to denser regions that would eventually form galaxies and galactic clusters. With the incorporation of cosmic inflation into the Big Bang model, it was theorized that the early universe would be largely uniform, punctuated by minor imperfections stemming from quantum ripples that were stretched into subtle variations in density. These minute variations were deemed critical. They were posited to be the imperfections that facilitated the formation of cosmic structures. After all, a perfectly smooth universe would remain eternally smooth. Galaxies require gravitational irregularities, uneven distributions, and clumps of matter to draw in gas and stars. Without these nascent flaws, there would be no material to assemble into stars, planets, or ourselves. Indeed, these imperfections are observable in the cosmic microwave background, CMB, manifesting as faint temperature fluctuations, the residual signatures of those primordial seeds. While the CMB clearly displays these minute variations as expected, the images of the early universe captured by James Webb do not seem to reveal the level of turbulence that those seeds should have engendered. Webb is observing a universe that is too smooth, too symmetrical, and too tranquil to exhibit clear signs of a cosmos still actively assembling its structure. This smoothness is not the kind that signifies uniform distribution across space. It's not that galaxies are evenly spread. Rather, they are appearing in locations, quantities, and configurations that are difficult to predict. The issue lies more with the rate and organization of structure creation, which appear too refined and advanced for such an early epoch after the Big Bang. Galaxies are manifesting with ordered spins, and clusters are coalescing in a remarkably consistent manner. The cosmic landscape is less chaotic than theory would suggest, a finding that is profoundly unsettling. According to the inflationary model, these fluctuations should have resulted in clumpy distributions in the early universe, with regions of higher and lower density gradually collapsing to form increasingly intricate arrangements. However, Webb is detecting galaxies that appear to have circumvented this chaotic process. In certain observed fields, there is a surprising homogeneity in both size and shape. Structures that should have taken billions of years to form seem to be already established mere hundreds of millions of years after the Big Bang. This predicament resonates with the critique some scientists have leveled against inflation, that it resolved too many pre-existing issues within the universe's initial state. Inflation might have rendered the universe overly smooth by expanding space so rapidly and efficiently, leaving insufficient room for structure to develop in the manner we observe. If this were the case, the galaxies observed by Webb should not exist. Yet, they are demonstrably present. Some researchers have proposed that our understanding of early gravitational collapse may be flawed, suggesting that gas and dark matter coalesce more rapidly than anticipated. However, this hypothesis also faces limitations. Gravitational systems inherently require time to grow. Even if we significantly enhance star formation efficiency or postulate unusually cold, dark matter, these adjustments do not readily account for the scale of structure being observed. Others point to the possibility that our cosmological simulations, used to predict structural formation, may be oversimplified. Perhaps the universe does not evolve in the manner we have programmed into our models. However, if this is true, it casts doubt on the reliability of decades of predictions based on these models, including the very shape of the early universe. There is also the potential that the observed smoothness is an artifact of our observations, an illusion suggesting that we are seeing galaxies that formed exceptionally early due to unknown physical processes, while the rest of the universe lagged behind. However, the more Webb surveys the early cosmos, the more untenable this explanation becomes. The observed anomalies are occurring with too great a frequency to be dismissed as rare statistical flukes. Another cosmic enigma, closely related to the too smooth problem, is the question of why the large-scale structure of the universe is so perfectly balanced. How is it that the rate of expansion, the distribution of matter, and the curvature of spacetime are all so precisely aligned to facilitate galaxy formation in the first place? Scientists had believed that inflation would provide an explanation for this finely tuned state, but Webb's findings suggest that this precision might exceed even inflationary predictions. It is almost as if the universe possessed an innate blueprint. What if the early universe was not a chaotic entity that eventually gave rise to order, but rather something akin to a pre-assembled system, a cosmos that did not build complexity but began with it already encoded? Such a scenario would necessitate a reevaluation not only of structure formation, but also of the universe's initial conditions, or perhaps an absence of a singular beginning altogether. James Webb and the impossibility of early galaxies. It was only a matter of time before some observers declared them impossible. This is not meant in a poetic or figurative sense. Rather, it signifies that their existence contradicts established physical laws. The initial deep-field images captured by the James Webb Space Telescope revealed galaxies that deviate significantly from theoretical expectations. They are too massive, too luminous, too ancient, and, most disturbingly, far too numerous to fit within the timeframe predicted by the Big Bang model. Astronomers had anticipated that Webb would discover nascent structures, small, chaotic, gas-rich clouds in the process of evolving into galaxies. They expected to witness the nascent, untidy stages of order, with stars just beginning to ignite and structures slowly coalescing over hundreds of millions of years. Instead, they observed fully formed galaxies shining brightly at redshifts of 10, 12, and even higher. These were galaxies that existed when the universe was merely a few 100 million years old. These galaxies were not merely surprising because they existed. They were deemed impossible due to the advanced stage of development they had already achieved. Some contained as many stars as our Milky Way. Others exhibited well-defined disk structures, stable rotational patterns, and chemical compositions indicative of multiple generations of stellar evolution. They did not resemble infants. They appeared as mature entities existing within a toddler universe. The James Webb Space Telescope has detected a galaxy, designated Sears 93316, exhibiting a redshift of approximately 16.7. This observation implies we are viewing this galaxy as it existed merely 240 million years after the Big Bang. This discovery presents a profoundly perplexing scenario. Existing cosmological models posit that this galaxy should not have had sufficient time to even initiate the formation of its initial stellar population, let alone mature into its current state. Nevertheless, there it is, clearly discernible, remarkably structured, and brilliantly illuminated. The classification of these galaxies as improbable is not solely due to their early cosmic appearance. It stems from the fact that the established timescales for stellar genesis, mass accretion, and the organization into complex cosmic structures are firmly rooted in well-established physical principles. Gaseous nebulae necessitate considerable periods to cool and undergo gravitational collapse. The process of star formation is contingent upon achieving specific density thresholds and overcoming gravitational instabilities. The enrichment of the cosmos with heavier elements, known as metals, requires the cyclical birth and demise of multiple stellar generations. These fundamental cosmic processes are inherently time-consuming and cannot be significantly accelerated. Yet, these particular galaxies appear to have accomplished all of this within the initial 2% of the universe's entire existence. Initially, upon receiving preliminary data from the Webb telescope, many astronomers assumed certain galaxies were being misidentified. They suspected their redshift measurements might be erroneously high, possibly due to photometric ambiguities or interference from nearby celestial objects. However, as spectroscopic confirmations began to materialize, the stark reality became undeniable. These high redshift values were indeed accurate, and the galaxies themselves were genuine. This confluence of evidence has ignited a growing consensus within the astrophysics community. Our current understanding of cosmic evolution requires fundamental revision. Some theorists have proposed adjusting the rates of star formation, suggesting that these early galaxies were far more efficient at converting interstellar gas into stars than their modern counterparts. Others have posited the existence of a novel category of extremely dark halos that could have facilitated accelerated gravitational collapse. However, these proposed modifications offer only partial solutions and introduce new quandaries. If star formation were indeed that efficient, why do we not observe similar phenomena in more recent cosmic epochs? If mass collapsed with such alacrity, what does this imply about the fundamental nature of dark matter or the influence of hitherto unknown forces? And perhaps most critically, why did our existing models fail to predict such an outcome? This is the persistent question that continues to resurface. For many decades, cosmological simulations have served as the bedrock for our expectations regarding the appearance of the early universe. We constructed a theoretical framework, known as the lambda-CDM model, which outlined when galaxies should form, their expected sizes, and their evolutionary trajectories. However, the Webb telescope has dramatically unveiled a cosmic stage already populated with actors, seemingly well before the play was intended to commence. The unease among scientists stems not merely from the presence of these celestial bodies, but from the profound implication that our entire conception of the universe's structure, particularly concerning its temporal evolution, might be fundamentally flawed. If the early universe was characterized not by a gradual accumulation of complexity, but by an abrupt transition into it, what else have we misunderstood about this nascent period? presently, the challenge posed by these impossible early galaxies represents one of the most significant and intensely debated enigmas in the field of astronomy. Furthermore, this is not an isolated anomaly. It signifies a potential disruption of the entire cosmic timeline, necessitating either a radical reevaluation of our current theories or the development of an entirely new cosmological model. The concept of cosmic dawn, the period when the first stars and galaxies ignited, is challenged by observations suggesting a universe that appears ready-made, rather than gradually evolving. Modern astronomy generally operates under the principle that complexity emerges and increases over vast stretches of time. Galaxies are not envisioned as instantaneously appearing, akin to a light switch being flipped on. Instead, they are understood to evolve, commencing as diffuse clouds of hydrogen and helium, coalescing under the influence of gravity, igniting their first stars, accumulating additional mass through stellar remnants, and slowly transforming into the intricate, dynamic structures we observe today. This evolutionary process, from simplicity to complexity, is theorized to unfold over billions of years. However, the data from the James Webb Space Telescope offers a contrasting perspective, one where the early universe did not undergo gradual change but rather emerged in a remarkably complete state. In virtually every deep-field image captured by Webb, galaxies are being identified that appear fully formed. They are not depicted in the process of assembly or on the cusp of becoming something else. They are already present, exhibiting star formation rates comparable to those of modern galaxies, possessing distinct structures like galactic disks, bulges, and spiral arms, and displaying chemical signatures that indicate multiple cycles of stellar material recycling. These are not nascent sketches but polished masterpieces, appearing mere hundreds of millions of years after the purported Big Bang. According to our established models, the cosmic dark ages, the period spanning from the emission of the cosmic microwave background radiation to the formation of the first stars, should have lasted approximately 200 to 300 million years. During this era, the universe was in a state of cooling, and gravity was slowly initiating its influence on the first neutral atoms. Following this phase, the earliest stars and galaxies were anticipated to begin their formation, characterized as being rudimentary, deficient in heavier elements, and relatively small. Yet, what Webb is revealing instead is a universe that appears to have bypassed this period of awkward adolescence entirely. Some of these galaxies possess stellar masses comparable to that of the Milky Way. This implies an extraordinarily rapid rate of star formation, converting gas into stars with an efficiency that current theoretical models cannot support. Even the most aggressive starburst scenarios, which describe events triggering intense periods of star formation, fall short of explaining the existence of galaxies of such magnitude at such an early cosmic stage. If galaxies formed with such speed and completeness, it fundamentally challenges the established timeline of cosmic evolution, potentially by orders of magnitude. This raises the disquieting possibility that the universe's narrative was not one of slow unfolding but rather a prescripted sequence of events, replete with structure, awaiting observation. What are the implications if the universe did not evolve gradually but commenced in a state of advanced organization? The inherent appeal of the Big Bang model has resided in its explanatory power, providing a narrative for the transformation of simplicity into complexity. However, if complexity was present from the outset, the fundamental story changes. Instead of emphasizing emergence, we are confronted with a phenomenon closer to direct appearance. This does not necessarily imply supernatural intervention or design, but such notions naturally arise when scientific understanding encounters profound discrepancies. It could simply signify that our knowledge of the universe's genesis is insufficient. It is plausible that conditions in the early universe were vastly different from our current understanding. The physics governing the creation of cosmic structures might have been governed by different rules or laws that are no longer applicable. Alternatively, it is conceivable that our perception of time, particularly in the universe's initial moments, is inaccurate. It is also possible that the temporal and spatial measurements themselves are flawed. If redshift is not a wholly reliable indicator of cosmic age, and if estimates of distance and time scales are imprecise, then these galaxies might not be as ancient as they appear. While this offers a potential window of explanation, it is only a temporary one. Even the most accommodating recalculations cannot extend a few 100 million years into the billions of years required for evolutionary processes to yield such complexity. Moreover, the remarkable uniformity observed among these early galaxies exacerbates the enigma. The presence of isolated pockets of premature complexity would already be extraordinary. However, Webb's findings suggest a consistent pattern, not a handful of rogue galaxies defying the rules, but entire populations exhibiting similar characteristics. This consistency strongly indicates that this was not an isolated occurrence, but rather the prevailing norm. Consequently, some cosmologists are beginning to articulate that the early universe resembles a stage already meticulously set. Upon the illumination of the lights, the actors are already costumed and delivering their lines, having bypassed any rehearsal or preparatory phase. The implication is a universe that was instantaneously ready, organized, and operational. This depiction is inherently difficult to reconcile with a cosmological model predicated on gradual development. It suggests that whatever processes were operative in the early universe were significantly faster, more efficient, and more organized than anything accounted for within the standard cosmological paradigm. The question arises, was it truly the cosmic dawn, or perhaps cosmic noon? For decades, astronomers have eagerly anticipated the opportunity to observe the epoch of cosmic dawn, the moment when the very first stars came into existence, effectively ending the cosmic dark ages and illuminating the nascent universe. At that presumed time, the cosmos was expected to be characterized by a profound quietude and uncertainty. Stars were anticipated to be sparsely distributed across the vast expanse, igniting within a sea of neutral hydrogen to give rise to the initial galaxies. This gradual transition from darkness to light was envisioned as our window into the genesis of cosmic form. However, with the advent of preliminary data from the James Webb Space Telescope, a disquieting possibility has emerged. What if the universe's dawn was not its beginning but rather occurred midway through its day? What if what we perceived as the gentle sunrise of creation was, in fact, the midday of a cosmic cycle, vibrant, active, and far more advanced than any origin story had previously suggested? The term, cosmic dawn, inherently implies a genesis, the first glimmer of light, the tentative commencement of an evolutionary process. Yet, the galaxies observed by Webb at redshifts of 10, 12, and even 16 are neither hesitant nor dim. They are luminous, structured, and dynamic, actively forming stars at rates comparable to those of present-day galaxies. Some of these ancient galaxies even outshine those that exist billions of years later. This is not merely a fleeting flicker in the void, but a brilliant conflagration. This revelation transcends mere aesthetic appreciation. It fundamentally contradicts our established understanding of the universe's history. We had anticipated a slow, incremental emergence of complexity, unfolding over successive generations. Instead, Webb presents a universe that appears to have bypassed its initial stages and leaped directly to its mature state. These early galaxies are not only bright but excessively so. They are forming at an unprecedented pace and exhibit a striking synchronicity with one another. They are observed ubiquity across the celestial sphere, not as isolated anomalies, but as part of a cohesive collective. They possess sophisticated features such as galactic disks, significant metallicity, and organized motion, all of which require considerably more time for formation, material recycling, and structural development than the Big Bang timeline permits. The implications are profound. If these observations accurately depict cosmic noon, it suggests that what we have designated as the early universe may not be early at all, at least not in the temporal framework we currently comprehend. It is conceivable that prior to the Big Bang, the universe was already well into a preceding phase of its existence. It is also plausible that the emergence of light was not an absolute beginning but rather a reinitiation, a reset, or a reillumination. Certain theoretical frameworks, including models of a cyclic or bouncing universe, propose that our current universe represents just one phase within an unending sequence of expansions and contractions. Within these models, the Big Bang is not viewed as the commencement of existence, but as a transition point, analogous to the chiming of a clock marking the start of a new hour, rather than the absolute beginning of time itself. Webb's observations may lend empirical support to these speculative ideas. If galaxies are already thriving at redshifts exceeding 12, then what preceded them? What provided them with the initial structures? What conditions facilitated such rapid star formation and complex organization? Entropy provides another avenue of inquiry. According to the fundamental principles of thermodynamics, entropy tends to increase over time, signifying a progressive buildup of disorder. If the universe began in a state of high temperature, density, and homogeneity, it should naturally evolve towards greater disorganization. However, Webb's observations reveal a remarkable degree of early organization, characterized not by chaos but by sophisticated structure. This inherent order suggests either a hitherto unrecognized low-entropy state or a residual memory from an earlier cosmic cycle that is somehow imprinted upon the current one. Some scientists are even contemplating the possibility that what we are witnessing is not merely early light but inherited light, meaning that the structure and organization we observe today originated from a period preceding the Big Bang. In this perspective, the cosmic dawn is not the world's inaugural breath, but rather the moment the curtain fell after an intermission. While these are currently speculative interpretations, Webb's research is nascent, and the understanding of its implications is continually evolving. However, the discernible trend is difficult to ignore. The sheer abundance of luminous and diverse early galaxies defies the notion of a slow, deliberate dawn. They exhibit characteristics more indicative of a universe that is already fully awake and well into its developmental phase. This necessitates a re-examination of fundamental questions, not only concerning when the universe began, but also the very nature of beginnings. If what we presume to be the middle of a cosmic narrative turns out to be its commencement, then either our perception of time is flawed, or we are interpreting the wrong chapter of cosmic history. Revisiting the steady-state theory, an alternative cosmological model existed prior to the Big Bang theory that proposed a different understanding of the universe's origin. Developed in the late 1940s by Hermann Bondi, Thomas Gold, and Fred Hoyle, the steady-state theory posited a universe without a discernible beginning or end. While this model acknowledged the universe's expansion, it proposed a continuous creation of new matter to maintain a constant average density. This concept eliminated the need for a singular, explosive origin, portraying a universe that was, on the largest scales, uniform in appearance and unchanging throughout time. For several decades, the steady-state theory stood as a formidable contender against the Big Bang model. It appealed to a philosophical inclination for an eternal universe, one that remained consistent at macroscopic scales, and was free from the potentially unsettling notion of a definitive beginning. However, in the 1960s, a critical blow was struck with the discovery of the cosmic microwave background radiation, CMB. This faint, uniform glow of residual heat, predicted by the Big Bang theory, proved exceedingly difficult to reconcile with the tenets of the steady-state model. Consequently, the Big Bang theory emerged as the dominant cosmological paradigm, relegating the steady-state theory to the realm of outdated scientific thought. until now. The recent findings from the James Webb Space Telescope are prompting a quiet reassessment among some scientists. While Webb is not outright disproving the Big Bang, it is revealing significant inconsistencies. The observations include galaxies forming at unexpectedly early times, stars exhibiting impossible elemental compositions, and black holes appearing far earlier than predicted by the Standard Model. These findings suggest a universe that is not young and nascent, but rather ancient and organized, existing at a far earlier epoch than currently allowed by standard cosmological timelines. These observations bear an uncanny resemblance to a universe that has been in existence and operational for an extraordinarily long period, rather than one that originated from scratch a mere 13.8 billion years ago. While the steady-state theory does not fully account for all of Webb's discoveries, it offers a more coherent framework for understanding the presence of enduring organization. Within this model, there is no imperative to rapidly explain the formation of galaxies or the accelerated growth of black holes. If the universe has always existed, then complexity can emerge gradually and perpetually across infinite time, without a defined beginning or end. However, the steady-state theory still faces challenges. The existence of the CMB remains a significant hurdle, and reconciling it with the concept of continuous matter creation is problematic. Nevertheless, some cosmologists are beginning to explore the possibility of integrating the strengths of both models. They ponder whether the early universe did not originate from a singular event, but rather emerged from a preceding cyclical process. They question if what we are labeling as early might actually be a later stage in a grander cosmic narrative. Modern variations of the steady-state theory build upon this concept. The quasi-steady-state cosmology, QSC, proposed by Hull and others later in their careers, introduced the notion of periodic mini-bangs, localized creation events occurring within an eternal framework. In the current era of Webb's observations, this concept appears less far-fetched. The galaxies observed at high redshifts do not resemble primordial galaxies. Instead, they suggest the latest in a long evolutionary lineage, potentially emerging from cosmic conditions already enriched by immense timescales. Webb has also complicated our assumptions regarding cosmic expansion. If the universe's expansion does not adhere to the predictable exponential trajectory we once assumed, and if it is influenced by unknown physics, phantom energy, or quantum effects, then the entire temporal calibration of the Big Bang model may be inaccurate. A universe that expands more slowly or cyclically would provide extended periods for the formation of early structures, thereby lending credence to the long-term evolutionary perspective inherent in steady-state ideas. It is important to note that few cosmologists advocate a complete return to the original steady-state theory. However, they are increasingly inclined to re-examine its core concepts in light of new data, recognizing the scientific imperative to explore alternative explanations when the prevailing model begins to exhibit strain and diminishing predictive power. Plasma cosmology. Was the universe born from energy, not a bang? Coexisting with standard cosmology, a controversial yet persistent alternative theory challenges not only the timing, but also the very mechanism of the universe's inception. This perspective, known as plasma cosmology, rejects the notion of a singular bang. Instead, it posits energy as the fundamental initial element. Plasma cosmology suggests that the universe is not primarily governed by gravity but by plasma, the force state of matter, and the electromagnetic forces that dictate its behavior. This model, partly developed by Nobel laureate Hannes Alfvén, proposes that the cosmos is a perpetual interplay of charged particles, vast electrical currents, and magnetic fields operating on cosmic scales. Whereas the Big Bang model describes a hot, dense, explosive birth, plasma cosmology envisions a universe devoid of a beginning, characterized by continuous energy exchange within an infinite expanse powered by electrical forces. In a plasma-dominated cosmos, matter does not aggregate solely through gravitational attraction. Instead, charged particles respond to electromagnetic fields, which are exponentially stronger than gravity, an estimated 10 trillion times so. These fields possess the capacity to channel, shape, and organize matter into filaments, voids, and spiral patterns, precisely the structures observed in large-scale cosmic maps. The cosmic web of galaxies and clusters, rather than being a remnant of gravitational clumping from a primordial state, may instead be the product of immense electrical currents forming plasma filaments across space. For decades, plasma cosmology has been largely dismissed as fringe science, primarily due to its difficulty in explaining the cosmic microwave background radiation and its inability to replicate the redshift distance relationship accurately predicted by the Big Bang. However, the recent data from the James Webb Space Telescope is compelling cosmologists to reconsider. The galaxies observed by Webb are too young, too organized, and too massive to align with the temporal framework of a gravity-dominated universe. Conversely, they may align more plausibly within a universe where plasma plays a dominant role. Stars and galaxies could form at significantly accelerated rates in such a plasma universe. Rather than gas clouds gradually collapsing under gravity, plasma currents could rapidly draw matter into cohesive strands, with magnetic fields subsequently constricting them. This phenomenon is known as the Bennett pinch. These electromagnetic interactions could trigger intense bursts of star formation, leading to rapid elemental replenishment and the construction of galaxy-scale structures. Do you see a pattern? It is not coincidental that plasma cosmology predicted some of the phenomena that Webb is now discovering. This is not due to any inherent mystical property, but because its mechanisms inherently allow for speed and structural development without the protracted timescales necessitated by gravitational collapse. Given that plasma constitutes approximately 99% of the visible matter in the universe, encompassing everything from stars and nebulae to intergalactic space, this theory suggests we have been overlooking the primary architect of cosmic structure. The early galaxies revealed by Webb are not merely early. They are astonishingly complex. Some are arranged in filamentary structures that already exhibit embryonic forms of the cosmic web. Such order, such large-scale connectivity, should not be evident so soon if gravity alone were the principal force at play. However, within the framework of plasma cosmology, this is precisely what one would anticipate from a network of charged matter governed by electric currents operating on galactic and intergalactic scales. The question of redshift warrants further consideration. Plasma cosmology proposes an alternative explanation for this phenomenon. Rather than being solely a consequence of space stretching due to cosmic expansion, this model suggests that redshift could be caused by photons interacting with intergalactic plasma. This interaction would result in energy loss, as photons traverse vast distances through an electrically active medium. Such an interpretation would necessitate a revision of how we measure cosmic time and space, potentially implying that these ancient galaxies are not as distant or as early as currently believed. To be clear, plasma cosmology remains a highly contentious subject. It lacks the widespread consensus enjoyed by the Big Bang model. Its explanation for the CMB is considered inadequate, and its capacity to generate predictive forecasts that align with current observations has been limited. Nevertheless, some cosmologists are now bravely posing the question, was it a misstep to disregard the role of plasma? Webb's discoveries are systematically challenging established models. There is also a cultural dimension to this scientific debate. Plasma cosmology has historically been relegated to the periphery, never receiving the prominent attention afforded to the Big Bang theory. This concept briefly resurfaced in the middle of the 20th century before fading, not because it was refuted, but due to the ascendancy of the Big Bang theory, which possessed momentum, institutional backing, and the mathematical elegance derived from inflation and general relativity. Plasma cosmology lacked this sophisticated mathematical framework. Instead, it dealt with the messy, dynamic realities of the physical world, characterized by chaos, nonlinearity, and modeling difficulties. However, it's possible that the universe itself operates in such a manner. The James Webb Telescope is currently unveiling a layer of the cosmos previously unseen, and what it reveals might not be the residual effects of a singular explosion, but rather the intricate patterns of a dynamic, electrically charged cosmos, shaped by forces far more immediate than ancient cataclysms. This presents a dichotomy: Big Bang versus Big Bounce, a universe potentially without a definitive beginning. For close to 100 years, the Big Bang has been the prevailing explanation for the origin of everything, postulating an explosive genesis from a single point, from which all of space, time, and matter emerged in an unfathomable manner. It is estimated that time commenced approximately 13.8 billion years ago, with the cosmos subsequently undergoing cycles of expansion and contraction. But what if this narrative is incomplete? What if the universe has been in perpetual motion throughout eternity, never truly having a starting point? Welcome to the realm of the Big Bounce, a radical alternative to the Big Bang theory that proposes our universe is merely the most recent phase in an eternal cosmic cycle of expansions and contractions, an endless heartbeat echoing across time. It's not a singular detonation, but an ongoing rhythm where the universe contracts into itself before rebounding into a new phase of expansion. Now, as the James Webb Telescope probes deeper into the cosmic past, certain scientists are beginning to question whether the accumulating evidence aligns better with a cyclical model than a linear one. The concept of a singularity, a point of infinite density and temperature where the established laws of physics cease to apply, lies at the core of the Big Bang theory. This mathematical anomaly, a moment when our equations become inoperable, is crucial to the Big Bang idea. The Big Bounce, however, eliminates the need for such a singularity. From this perspective, the universe never truly perishes. Instead, it compresses to an infinitesimal size before expanding anew, driven by quantum effects, the pressure exerted by exotic forms of matter, or unknown physical principles governing gravity at extremely minute scales. Why reconsider this idea now? Because the discoveries made by the James Webb Telescope are challenging the notion of a linear cosmic timeline. The existence of massive, well-structured galaxies appearing far too early in the universe's history, seemingly bypassing crucial evolutionary stages, suggests a pre-existing order, perhaps even a residual memory from a prior cosmic iteration. In a cyclical universe, each phase leaves behind patterns and information that influence the subsequent cycle. This might explain why galaxies observed from the early universe appear so highly developed. They are not anomalies, but inheritances, complexities carried over from a previous cosmic epoch that collapsed, reset, and then sowed the seeds for the universe we inhabit today. This is not mere speculation. The Big Bounce is more than a hypothesis. The concept of a quantum bounce replaces the Big Bang singularity in quantum gravity models, particularly those derived from loop quantum cosmology. According to these models, when space reaches extreme densities, quantum effects exert a repulsive force, halting the collapse and initiating a new phase of expansion. Time cycles, it does not terminate. Furthermore, there is observational support for this idea. The remarkable uniformity and structure of the cosmic microwave background radiation, along with the early emergence of galaxies observed by Webb, can be interpreted as indicators of an antecedent order. If the universe is considerably older than we currently believe, not 13.8 billion years old, but eternally ancient, then the rapid appearance of complexity requires no special explanation. It was already present. In a singular, one-off universe, entropy continually increases, eventually leading to a cold, uniform demise. However, in a bouncing cosmos, entropy may be reset or replenished with each cycle. Alternatively, the balance could occur in a manner that preserves structures across successive cycles, allowing galaxies, and even black holes, to leave their imprints on subsequent iterations. Naturally, challenges remain. A significant hurdle is thermodynamics. How does a universe that undergoes cyclical balances prevent chaos from accumulating indefinitely? Wouldn't each subsequent cycle be more disordered than the last? Some models propose that each bounce results in a slightly larger universe, thereby dispersing the chaos. Others resort to speculative mechanisms, such as exporting entropy into parallel dimensions or branes, concepts rooted in string theory. Another critical question is whether we can empirically verify this hypothesis. To detect evidence of a prior universe, we would need to search for residual marks within our own cosmos, such as anomalies in the microwave background, peculiar anisotropies, or lingering gravitational waves. Some cosmologists believe these traces might already exist, subtly embedded within the data and perhaps misidentified as noise or other unexpected phenomena. The increasing consideration of the tired light hypothesis, an alternative to the prevailing notion of cosmic expansion, is noteworthy. For an extended period, redshift has served as the primary method for determining the distance to galaxies. The farther a galaxy is, the longer ago it emitted the light we observe, and consequently, its light is more stretched towards the red end of the spectrum. This concept is so deeply ingrained in modern astronomy that it is often accepted as an unassailable fact, with redshift equating to expansion, which in turn validates the Big Bang. But what if this interpretation is incorrect? An older, long-dismissed explanation, now experiencing a quiet resurgence in light of the James Webb Telescope's revelations, offers a different perspective: the tired light hypothesis. This theory posits that light's redshift is not a consequence of the universe's expansion, but rather a result of its energy loss over vast cosmic distances. In this view, photons, the fundamental particles of light, gradually lose energy as they traverse the fabric of space. This energy depletion causes their wavelengths to shift towards the red end of the spectrum, mimicking the effect of recession, but without any actual motion or spatial stretching. It simply describes light, tiring, like a depleted battery, as it journeys through an ancient, boundless cosmos. Fritz Zwicky first proposed this idea in the 1920s, a concept fundamentally at odds with the prevailing notion of an expanding universe. However, as the Big Bang theory gained wider acceptance, the tired light hypothesis receded from prominence. It faced criticism for failing to adequately explain certain observational data, such as the time-dependent stretching of light curves from distant supernovae, and for lacking a specific physical mechanism to account for light losing energy without becoming diffuse or blurry. Nevertheless, it never entirely disappeared. And now, with the James Webb Telescope revealing galaxies that appear remarkably mature for their observed redshift, the tired light model is once again attracting quiet attention. If these galaxies are not as distant or as ancient as their redshift suggests, then the entire established timeline of the universe collapses, and many of the Big Bang's most profound enigmas may be resolved. Within the framework of the tired light theory, the early, massive galaxies detected by Webb might not be as ancient as they appear. Their significant redshift, rather than marking a temporal distance, would represent the cumulative energy lost by their photons. This would imply that the universe is not receding from a central point, but is instead static, or perhaps even infinite and eternal. Galaxies would not be fragments launched from a singular origin, but rather objects inherently present, spread throughout space-time, their light aging as it reaches us. From this viewpoint, some of the challenges posed by Webb's observations can be elegantly addressed. These galaxies would have had ample time to develop, meaning they are not growing too rapidly, nor are black holes forming prematurely. They are simply very old, their evolution having been a gradual, consistent process. The elemental composition of stars within these galaxies would not contradict prevailing models of galaxy formation, but would instead indicate an universe of immense age. The tired light hypothesis continues to face criticism. A primary objection is the absence of observable blurriness. If interactions cause photons to lose energy, wouldn't they disperse, rendering distant galaxies indistinct? However, contemporary versions of the theory propose more subtle mechanisms for energy loss, such as quantum-level energy leakage or interactions with an as-yet undiscovered feature of the vacuum. The cosmic radio background also presents a challenge. Within the Big Bang model, this radiation is understood as residual energy from a hot, dense early state. The tired light hypothesis currently lacks a direct, universally accepted explanation for this phenomenon. Some proponents suggest that what we perceive as the cosmic microwave background could be reinterpreted as steady radiation within an eternal universe, or as the cumulative emission from extremely distant galaxies that has dispersed over time. These remain speculative, but are no longer considered outlandish. What lends renewed relevance to the tired light concept is the precision of the Webb telescope. We are now observing distant galaxies with unprecedented detail, and their apparent maturity is difficult to reconcile with a standard timeline driven by expansion. If the fundamental assumption of that timeline, that redshift equates to distance, is flawed, then our entire cosmological chronology is called into question. The resurgence of the tired light idea is not motivated by nostalgia or a desire to be contrarian. Instead, it stems from a fundamental question: have we mistaken a measurement for a meaning? Redshift might indeed convey information, but its precise interpretation remains an open inquiry. The James Webb Telescope was not designed to prove or disprove the tired light hypothesis. However, its observations, galaxies exhibiting excessive maturity, structures appearing too organized, and timelines appearing too compressed, are breathing new life into long-standing doubts. These doubts suggest that our interpretation of light's journey across space may be more a product of human perception than a reflection of universal reality. How the James Webb Telescope challenges interpretations of the cosmic microwave background. For many years, the cosmic microwave background, CMB, has been lauded as the most compelling evidence for the Big Bang. It represents the oldest light we can detect, originating from a period when the universe had cooled sufficiently for atoms to form, allowing photons to travel unimpeded. This steady glow, first observed in 1965, is often referred to as the afterglow of creation, or a snapshot of the universe in its infancy, frozen in time approximately 380,000 years after the Big Bang. But what if our understanding of this snapshot is fundamentally flawed? While the James Webb Space Telescope, JWST, is not directly designed to observe the CMB, as it is tuned to infrared, not microwave, wavelengths, it is capable of observing the epoch immediately following it. By peering into the era of the first stars and galaxies, Webb effectively bridges the observational gap between the CMB and the present-day universe. And this bridge is beginning to show cracks. The issue lies in the CMB's prediction of how the cosmic framework should evolve. Satellites like COBE, WMAP, and Planck have meticulously mapped minute temperature variations within the CMB. These variations are believed to be the quantum seeds from which all cosmic structures subsequently grew. From these patterns, we have gleaned insights into the universe's matter content, its early lumpiness, and the types of structures we should expect to observe at different epochs. However, the James Webb Telescope is consistently detecting more structure, greater complexity, and larger objects at earlier times than theories based on the CMB would predict. This presents a significant discrepancy. If the CMB truly represents the initial conditions of the universe, then how did such rapid and organized formation occur? The implication is either that our understanding of how matter evolved from the CMB is incomplete, or that the CMB itself does not tell the entire story. A key concern revolves around the scale of these initial fluctuations. The CMB exhibits temperature variations of merely 1 part in 100,000, indicating an astonishingly smooth early universe. This uniformity has long been a source of perplexity, as such an evenly distributed matter would seemingly require an immense amount of time to evolve into the clumpy arrangement of stars, galaxies, and filaments we observe today. This is precisely why the theory of cosmic inflation was developed. It proposes a mechanism to rapidly expand and smooth the early universe, preserving just enough initial imbalance to facilitate structure formation. Yet, Webb's early galaxy discoveries appear too lumpy and too early. It's as if the seeds of structure were larger or grew at a pace exceeding what the CMB suggests. This points to two potential scenarios. Either structure evolved independently of the initial CMB fluctuations, or the conditions we assumed existed at the universe's outset were not actually present. Another troubling observation is the CMB's remarkable isotropy, meaning it appears uniform in all directions. However, Webb has identified regions of the sky with an unusual abundance of early galaxies. This could indicate that the CMB failed to capture certain localized differences, or that the fundamental assumption of large-scale homogeneity in the universe is incorrect. If the early universe was not as smooth as the CMB suggests, then either an intervening event occurred between the CMB epoch and the formation of the first galaxies, or the CMB is an inaccurate representation of the past. A more profound concern is the possibility that we fundamentally misunderstand the CMB itself. Alternative models propose that the microwave background might not be a remnant of the hot Big Bang, but rather the cumulative product of processes occurring over a vastly extended period. In certain quasi-steady state and plasma cosmology models, the CMB is not viewed as the afterglow of creation, but as an equilibrium background radiation, comprised of emissions from stars, galaxies, and black holes that have been dispersed and redshifted over eons. Even within the Big Bang model, discrepancies persist. The Hubble tension, the disagreement between the universe's expansion rate as measured by the CMB and as measured by nearby galaxies, remains unresolved. While Webb's data is refining the local expansion rate, it simultaneously highlights a fundamental issue with our predictions of the early universe, derived from CMB physics. This suggests that the very fabric of space and time may be more intricate than we currently comprehend. Although the James Webb Telescope was not constructed to measure the CMB directly, by observing the universe's actual evolution from its supposed starting point, it has become a mirror, reflecting not only the predictions of the CMB, but also its potential limitations. Early galaxy metallicity, stars that shouldn't exist. Within the grand narrative of cosmic evolution, the very first stars were expected to be relatively simple. These so-called population 3 stars were theorized to be massive, short-lived, and, crucially, devoid of metals. They were believed to have formed from the primordial hydrogen and helium forged in the early universe. In astronomical parlance, metals refer to any elements heavier than helium. These elements are synthesized only through nuclear fusion within stars and subsequent supernova explosions. Since metals had not yet been produced, it was logical to assume the first stars would have been metal-free. A glance at a relevant chart would reveal metals as indicators of time. Their presence signifies a later stage in cosmic history. However, as the Webb telescope gazes deeper into the early universe, it has detected galaxies with metal abundances significantly higher than predicted. Some of these galaxies exhibit metallicities comparable to, or even exceeding, that of our own Milky Way. Furthermore, they appear remarkably early, identified at redshifts exceeding 10, indicating they existed when the universe was only a few 100 million years old. Within this time frame, multiple generations of stars should not have had sufficient time to live, die, and disseminate metals throughout the cosmos. Yet, here they are, chemical signatures that seem out of place for this epoch. This is not a minor anomaly. It fundamentally challenges our understanding of stellar and galactic evolution. Our previous assumptions suggested that the early universe lacked the necessary elemental building blocks. The expectation was that the first stars would burn intensely and briefly, then explode, creating the initial instances of iron, carbon, oxygen, and other heavier elements. We would not anticipate observing stars and galaxies rich in metals until the cycle of stellar birth, death, and metal enrichment had occurred multiple times. However, Webb has discovered these metal-rich galaxies not only early on, but also widely distributed, not as isolated exceptions, but as entire populations exhibiting substantial chemical complexity. The issue is not merely the presence of metals, but the implication that stellar evolution was somehow accelerated, or that it did not proceed as we had previously conceived. If the initial stars were exceptionally massive, they might have completed their life cycles and died even more rapidly than anticipated, enriching their surroundings in a mere tens of millions of years. However, this scenario requires a remarkable degree of efficiency. Supermassive stars forming immediately after the Big Bang, exploding in precisely timed waves, and triggering subsequent generations of star formation without delay. While not impossible, this sequence of events seems highly choreographed and improbable. There is also the possibility that metals were synthesized prior to the Big Bang, either within a preceding cosmic era or as a rebound from an earlier universe. From this perspective, the universe we observe is not the initial step in cosmic development, but rather a continuation. Webb's findings of early metallicity do not necessarily prove accelerated evolution. They could instead indicate transmission from a prior cosmic phase. This notion is particularly provocative in light of alternative cosmological models, such as cyclic models or the Big Bounce. In these scenarios, metals and structures can survive the process of cosmic collapse and be reconstituted in the subsequent expansion. Under this interpretation, ancient, metal-rich galaxies do not appear premature. They seem like seasoned survivors of a previous cosmic reality. Another unsettling question arises regarding the very existence of population 3 stars. Despite decades of searching, no metal-free stars have ever been observed. Every star we have detected, even those in the most distant reaches of the universe, contains some amount of metal. It is possible that population 3 stars never existed, or that they were so rare and short-lived that they left no discernible evidence. Even more profoundly, what if our understanding of the origin of the universe's chemical elements is entirely mistaken? Webb's remarkable sensitivity allows us to analyze the spectral lines of distant galaxies with unprecedented clarity, revealing a chemical narrative that increasingly diverges from the predictions of standard Big Bang nucleosynthesis. The deeper we probe, the more it appears that metals are intrinsically woven into the fabric of the early universe, like ink that was present in a book before the printing press was even invented. The high metallicity observed is not expected. So how should we reconcile this? We could adjust our models, envisioning extreme scenarios of rapid star formation or redefining what constitutes early. However, each such fix renders a model once praised for its elegance increasingly cumbersome. Alternatively, we might confront a more profound possibility, that the chemical past of the universe is not neat, linear, or young. Objects like stars and galaxies might be imparting knowledge about something far older than the Big Bang, something more complex than the timeline we have come to accept. Primordial gas clouds that defy the Big Bang model. It was once believed that the early universe was a simple place. As the cosmos expanded and cooled following the Big Bang, it was expected to transform into a vast expanse of neutral hydrogen and helium, the lightest elements forged in the initial minutes of cosmic nucleosynthesis. Hundreds of millions of years were thought to pass before gravity could coalesce these elements into the first stars and galaxies. During this period, known as the Cosmic Dark Ages, neither stellar fusion nor the death of stars was occurring, and the universe was chemically quiescent. However, thanks to the James Webb Space Telescope and other highly precise observatories, astronomers are now discovering primordial gas clouds that do not conform to this established narrative. These clouds are being found in the deep past, some more than 12 billion light-years away, and they exhibit characteristics that challenge virtually every assumption about the early universe. Their temperature, composition, structure, and density all raise uncomfortable questions. Firstly, there is the issue of metal content. Some of these gas clouds, which should theoretically be untouched by star formation, already display evidence of contamination by heavier elements such as carbon, silicon, or even iron. These metals should not be present. According to the standard Big Bang model, the only mechanism for producing these elements is through the life and death of stars. If these gas clouds are truly primordial, they should consist solely of hydrogen and helium. Their unusual metallic content hints at either contamination from a prior stellar generation we overlooked, or they predate the entire chronological framework we've established. Secondly, their measured density and temperature appear incongruous. Certain cosmic clouds exhibit a cooler than anticipated thermal state, suggesting a stability that should not manifest so early in the universe's existence. Conversely, others are hotter and denser, fueling the hypothesis of an unknown energetic influence or pressure at play. This opens the door to more speculative hypotheses, such as primordial magnetic fields or residual warmth from a preceding cosmic epoch, both of which lie outside the standard cosmological model. Furthermore, their structural characteristics are perplexing. In the nascent universe, gas was expected to be relatively uniformly distributed, with minor deviations solely due to quantum fluctuations imprinted during inflation. However, some gaseous formations being detected by instruments like Webb appear filamentary, aggregated, or even in a state of rotation, as if already on a trajectory towards galactic formation. Such structure typically requires significant time to develop through gravitational evolution, yet it seems present from the outset. This suggests either a far more rapid and efficient process for gas condensation and star birth than previously understood, or that these formations are not as young as their observed red shift might imply. A growing number of researchers are questioning whether redshift-based dating, which correlates higher redshift with greater distance and thus earlier cosmic times, might be providing a misleading interpretation for these specific phenomena. Could some of these gaseous nebulae actually be closer to us in cosmic time than their redshift indicates, perhaps influenced by presently unknown distorting factors? It is also noteworthy that these clouds occupy unexpected locations within the cosmic landscape. They do not consistently align with known galactic structures. Some appear in seemingly empty voids, while others lack any discernible connection to observable star-forming regions. Their extreme distance makes definitive identification challenging. Are they rogue galaxies, nascent galactic halos, or perhaps remnants from a prior, obscured era of cosmic development? A disquieting possibility is that some of these gaseous formations are vestiges from a preceding universe, remnants of a cosmic cycle that concluded in collapse and subsequently initiated anew. In cyclical or bounce cosmological models, fragments of a prior cosmic iteration can persist and influence the evolution of the next. Consequently, these clouds might not merely be anomalies, but rather chemical and structural signatures of a universe that ceased to exist so that ours could emerge. Mainstream astrophysics is not yet prepared to embrace such a radical conclusion. However, the accumulating body of observational discrepancies can no longer be disregarded. These gaseous nebulae resist easy classification. They are neither pristine nor uniform, nor are they inert. They exhibit characteristics that suggest histories extending beyond the officially recognized inception of the universe. The prevailing cosmological paradigm posits an upward progression from fundamental simplicity. First hydrogen, then stars, followed by galaxies, and finally intricate structures. Yet, these gaseous formations appear to invert this hierarchy, arriving already shaped, enriched, and influenced. This compels us to confront the question of what preceded this perceived beginning. Alien civilizations and the Fermi paradox. A persistent inquiry has troubled scientists, philosophers, and stargazers alike. Where is everybody? This sentiment encapsulates the core of the Fermi paradox, highlighting the stark contradiction between the high probability of extraterrestrial intelligent life and the utter absence of any detectable signals. Each galaxy contains billions of stars, many of them significantly older than our own Sunday. This temporal advantage suggests that intelligent life should have had ample opportunity to develop, proliferate, and leave behind discernible traces. Yet, the universe remains silent. With the James Webb Space Telescope now peering into the early universe and revealing surprisingly mature galaxies, complex structures, and early signs of sophistication, the Fermi paradox takes on a more profound and somber dimension. If the universe consistently formed organized structures at an earlier stage than anticipated, then the potential for intelligent life, at least its very possibility, might have emerged billions of years prior. The data from Webb indicates that galaxies and stars were forming with remarkable rapidity, even within the first few 100 million years following the Big Bang. This implies that planetary systems could have coalesced much earlier than our current models predict, presenting opportunities for habitable environments. It is conceivable that civilizations rose and fell before Earth had even cooled, if our planet is a latecomer in the cosmic timeline. The Fermi equation has undergone a reevaluation. The question is no longer whether life exists elsewhere, but rather how civilizations might have had vast expanses of time, potentially eons, to develop, spread, and even transcend biological limitations. Therefore, the pervasive silence may not stem from a lack of life, but rather from a more profound, possibly unsettling, underlying cause. One possibility is that we are not alone, but simply isolated. Dark energy's accelerated expansion of the universe is causing galaxies to recede from each other at an ever-increasing rate. This makes communication, travel, or detection across vast cosmic distances not only impractical but physically impossible. Civilizations may have thrived and evolved, only to be inherently constrained from spreading by the very fabric of spacetime. Another chilling hypothesis suggests that civilizations are inherently transient. The same accelerated evolutionary processes that enable galaxies to mature early might also preordain rapid self-destruction. If early intelligent life emerged, it might have eradicated itself long before achieving interstellar communication capabilities. The more technologically advanced a civilization becomes, the greater its capacity for self-annihilation, whether through warfare, artificial intelligence gone awry, or ecological collapse. A further unsettling notion is that advanced civilizations transcend physical existence before venturing into interstellar space. Highly evolved beings might abandon the material realm entirely, migrating to digital substrates, quantum matrices, or simulated realities where they no longer interact with the observable cosmos. To them, our perceived universe could be mere background noise, akin to an untamed wilderness beyond a digital metropolis. Webb's discoveries do not invalidate these scenarios. Rather, they enhance their plausibility. By presenting a cosmos that achieved structure and complexity earlier than expected, it broadens the temporal window for the emergence and evolution of life, and consequently, the duration of cosmic silence. Then, there is the profoundly serious consideration: what if other civilizations have attempted to reach out, but we, in our nascent state, are simply incapable of detecting them? It is possible that indicators of intelligence are not limited to radio waves or monumental constructions, but might manifest as subtle alterations in quantum entanglement, gravitational lensing, or the cosmic microwave background radiation itself. Given our incomplete understanding of Webb's revelations about the universe, how could we possibly recognize the work of intelligences that have existed for billions of years? Finally, there exists a more optimistic perspective. Perhaps we have not yet encountered alien life because we are the first to arrive. Not merely the first humans, but the inaugural inhabitants of a still young and awakening world. While Webb's findings may point to early organization, they do not definitively prove the existence of life. It is possible that environments conducive to stable, carbon-based life are exceedingly rare. Perhaps habitability is not an inherent characteristic, but an exceptionally uncommon occurrence. In this scenario, we, a peculiar and perhaps fragile entity, could be the inaugural voice in an otherwise profoundly silent universe, a voice that may either fade into cosmic oblivion or initiate a dialogue spanning vast epochs. Did the universe truly begin? The notion of a distinct origin for the cosmos stands as a cornerstone of modern scientific thought. The Big Bang, envisioned as a singular, cataclysmic event, is credited with the sudden emergence of all time, space, and matter. It established a cosmic chronometer, a definitive starting point that anchors existence within a temporal framework amenable to study, dissection, and modeling. This allows us to scientifically address a question once relegated to philosophical contemplation. As the James Webb Space Telescope delves deeper into the cosmic expanse and probes earlier epochs, it increasingly reveals a universe that does not conform to the image of recent creation. Instead of observing the gradual assembly of galaxies, we are witnessing pre-established structures, stars already rich in heavy elements, and supermassive black holes firmly entrenched to galactic cores. This depiction is inconsistent with a nascent universe. It suggests an ongoing, perhaps protracted, evolutionary process. In classical physics, the concept of a beginning introduces a boundary where our established physical laws falter. The singularity of the Big Bang represents this ultimate limit, infinite density, infinite temperature, and an explanatory void beyond. Time is posited to commence at zero, with no antecedent. However, this is less a scientific pronouncement and more an acknowledgement of ignorance cloaked in mathematical formalism. Alternative cosmological models, once marginalized, are now gaining prominence. Some cosmologists propose that the Big Bang was not an absolute beginning but rather a phase transition, analogous to water solidifying into ice. The universe may have transitioned from a prior state, currently beyond our observational or theoretical grasp, where quantum fields or higher dimensions existed in a different configuration. Other theories posit that the universe has always existed, undergoing eternal cycles of contraction, expansion, and rebirth, devoid of any true commencement or cessation. The burgeoning field of quantum gravity research also suggests that spacetime itself might be an emergent property rather than a fundamental constituent. If this is the case, the very concept of a singular beginning becomes logically untenable, akin to inquiring about the origin of a lake surface without considering the constituent molecules. The impetus behind these evolving perspectives is not solely theoretical. It is increasingly driven by empirical evidence that challenges the conventional Big Bang framework. The galaxies observed by James Webb exhibit a level of development, mass, and chemical enrichment that is incongruent with a universe presumed to be in its cosmic infancy. The large-scale structures within the cosmic web display an unexpected degree of organization, and the stars appear remarkably mature. These observations do not merely strain the established timeline. They suggest that the timeline itself may be fundamentally flawed. What would the implications be if the universe did not have a singular beginning? It could imply a perpetual cosmic engine, constantly reconfiguring itself without a definitive starting point. It might suggest that our perception of time is merely a localized illusion, and that reality as a whole does not adhere to a linear progression. Some extreme theoretical frameworks even propose that the universe exists as a static, immutable block, where past, present, and future coexist simultaneously, and our subjective experience of a beginning is simply a consequence of our observational perspective. This revival of ancient philosophical debates prompts a fundamental question. Is the concept of creation indispensable? Is life itself a product of causality, or are we akin to aquatic organisms, oblivious to the surrounding ocean, compelled to perceive beginnings and endings due to the inherent structure of our cognitive faculties? This does not signify the obsolescence of the Big Bang theory. It remains the most robust explanatory model for numerous cosmic phenomena, including the cosmic microwave background radiation, the expansion of space, and the abundance of light elements. It compels us to ponder whether the Big Bang represents the true origin or merely the inception of phenomena accessible to our observation. Ancient philosophers theorized a timeless, unchanging, perfect mechanical universe. The advent of the Big Bang introduced the concept of cosmic birth. However, we may now be returning to our philosophical roots. It is conceivable that the universe has always existed in its current state. Rethinking spacetime. Is our model of reality flawed? For over a century, our understanding of reality has been dominated by Einstein's model of spacetime. This framework depicts a four-dimensional fabric where mass warps space, dictating the movement of matter, while time advances inexorably, like a cosmic clock. The predictive power of this model has been extraordinary, foreseeing phenomena such as black holes and gravitational waves, and enabling precise galactic mapping, trajectory calculations, and even accurate spacecraft navigation. However, as the James Webb Space Telescope extends our vision to the most distant reaches of the cosmos, a more profound and troubling question arises. What if spacetime itself is an illusion? The more we observe, the more the universe appears to defy the geometric constraints we previously attributed to it. From galaxies that form with a rapidity that spacetime should not permit, to stars that achieve maturity before time would conventionally allow, we are encountering behavior that deviates from the established model. At the heart of this growing dissonance lies a radical concept emerging from quantum physics. Spacetime may not be a fundamental aspect of reality. In this paradigm, what we perceive as space and time might be emergent properties, arising from a deeper substratum of existence, much like temperature emerges from the collective motion of molecules, or a hologram is formed from interference patterns. Time may not truly flow, and space may not genuinely expand. Instead, both could be coarse-grained perceptions, byproducts of a reality whose fundamental nature we have yet to adequately describe. This is not mere philosophical conjecture. It is grounded in theoretical frameworks such as causal set theory, emergent gravity models, and loop quantum gravity. These approaches propose that spacetime is composed of discrete, fundamental units, akin to quantum information bits interconnected through a deeper layer of reality. When the James Webb Telescope reveals a universe where structure seems to precede spatial extent, or memory appears to precede chronological age, it prompts us to question whether we are observing true spacetime or merely artifacts within its underlying code. The very concept of distance, a fundamental component of spacetime, is being challenged. Redshift, our primary tool for gauging cosmic distances, is predicated on the assumption of an expanding space over time. However, if this expansion is not real or is not uniform, our entire understanding of the universe's scale could be fundamentally inaccurate. Galaxies currently estimated to be 13 billion light-years away might, in reality, be significantly closer. They could also exist in locations not describable by conventional spatial dimensions. Consider quantum entanglement, a phenomenon where particles separated by vast distances appear instantaneously correlated. Some physicists interpret this not merely as a quantum anomaly but as an indication that distance itself is illusory. It suggests that 2 points can be intimately connected within a deeper, information-based reality, irrespective of their separation in our observable universe. If this is the case, space may be relational rather than absolute, with the universe's structure determined more by connectivity than by fixed coordinates. Time fares no better. In classical physics, time is absolute. In relativity, it is elastic, subject to dilation by gravity and velocity. However, within quantum mechanics, time often appears as a secondary consideration, not a fundamental variable but a parameter introduced by the observer. In certain formulations of quantum gravity, time is absent altogether. Existence is simply a state of being. What we perceive as change or causality is then reinterpreted as a narrative construct imposed upon a timeless web of relationships. If Webb's observations continue to show galaxies behaving as if time commenced earlier than expected or space was organized before its evolutionary capacity should allow, we may be compelled to reconsider a universe that operates independently of spacetime. The unsettling possibility is that the evidence for this paradigm shift may already be within our grasp. The holographic principle, which posits that all information within the universe might be encoded on a two-dimensional surface, is gaining traction. Phenomena such as quantum entanglement, black holes, and even dark energy could be manifestations of an illusory reality where spacetime is a construct and information is the fundamental currency. Quantum gravity and the early universe. Gravity, the most ancient of the fundamental forces known to humanity, has been described with increasing sophistication from Newton's celestial mechanics to Einstein's geometric representation of spacetime. It governs the cohesion of galaxies, the formation of black holes, and the orbital dance of celestial bodies. Despite its profound influence, gravity remains an enigma in the scientific landscape. Unlike electromagnetism, the strong nuclear force, and the weak nuclear force, gravity resists unification with the quantum realm, where uncertainty, entanglement, and probabilistic outcomes are paramount. This incompatibility becomes particularly acute when examining the universe's initial moments, the aftermath of the Big Bang, or whatever primal event marked its emergence. While the James Webb Space Telescope may not directly detect quantum gravity, its discoveries are compelling scientists to re-examine this elusive frontier. The telescope's observations of galaxies forming prematurely, stars rapidly accumulating heavy elements, and structures appearing without the anticipated scaffolding of spacetime, all point towards a deeper, more fundamental law of nature at play, one that a theory of quantum gravity is uniquely positioned to explain. At its core, quantum gravity seeks to reconcile general relativity with quantum mechanics, describing the behavior of gravity under extreme conditions of minute scales and immense energies, such as those present at the universe's inception or within black holes. However, traditional physics falters in these regimes. General relativity envisions a smooth, continuous spacetime, whereas quantum mechanics predicts fluctuations, uncertainty, and discrete informational units. Their attempted integration results in mathematical paradoxes, infinities, and untenable models. New theoretical frameworks are being constructed from the ground up to address this challenge. String theory proposes that fundamental particles are not point-like entities, but rather vibrating strings existing in up to 11 dimensions. By compactifying these extra dimensions, string theory aims to unify all known forces, including gravity, and introduces the concept of branes, higher-dimensional membranes that could contain entire universes. This framework also accommodates cyclical cosmological models. Loop quantum gravity, LQG, on the other hand, adopts a different approach. It postulates that space is granular, composed of discrete units, much like pixels on a screen. LQG suggests that space is not a uniform continuum, but rather a foamy network of tiny quantum loops. Concurrently, time, rather than flowing smoothly, evolves in tandem with this quantum network. A significant implication of LQG is that the Big Bang was not a singular beginning but a quantum bounce, a transition from a compressed, non-singular state to an expanding universe. These are not mere theoretical constructs. They are subject to empirical testing, and the James Webb Space Telescope may be bringing us closer to such verifications. For instance, if spacetime arises from quantum processes, the early universe should exhibit quantum characteristics such as deviations from smoothness, the formation of unusual structures, or peculiar light propagation patterns. Some of Webb's findings, such as galaxies forming at rates inconsistent with established models of structural evolution, could represent such quantum fingerprints. Even the presumed uniformity of the cosmos, traditionally attributed to cosmic inflation, might find alternative explanations within quantum gravity. Certain models suggest that quantum entanglement across pre-spacetime could account for the profound coherence observed in widely separated regions of the universe. These models imply that causality, as we understand it, may not have been operative during the universe's earliest epoch. In a pregeometric state, where distances had not yet emerged, everything could have been interconnected. A crucial insight from this perspective is that information might be more fundamental than matter or energy, and that patterns of quantum entanglement could actively shape the geometry of spacetime itself. From this viewpoint, the universe is not expanding into space. Rather, it is a vast quantum computation, a colossal network processing data into experiential reality. Therefore, when James Webb observes fully formed galaxies or supermassive black holes remarkably close to the universe's inception, it may not always indicate an issue with the instrumentation or data. In this domain, spacetime and gravity are not fundamental laws, but emergent effects, offering a potential glimpse into the quantum underpinnings of existence. The ultimate ambition in physics has long been the formulation of a theory of everything, capable of unifying all cosmic phenomena. However, it is possible that what is truly required is not a singular theory, but a fundamental paradigm shift. A new paradigm is emerging, shifting our perception of the cosmos from a realm governed by forces to a dynamic process unfolding from a quantum substrate. In this conception, origins are illusory, and gravity itself is not a prime mover, but a residual reverberation. The James Webb Space Telescope is at the forefront, challenging the venerable standard model of cosmology, specifically the Landesidium, cold dark matter, framework, a cornerstone of modern astronomical inquiry for many years. This prevailing model posits a universe originating with the Big Bang, detailing subsequent phases like inflation, the genesis of the cosmic microwave background, the large-scale distribution of galaxies, and the crucial, albeit mysterious, contributions of dark matter and dark energy to the universe's structure. It possessed an elegant explanatory power, capable of predicting phenomena and enduring numerous observational tests. The standard model, however, was always a synthesis, a carefully constructed narrative pieced together from disparate observations. It relied on fundamental assumptions: the smoothness and uniformity of spacetime on vast scales, the role of gravity in shaping cosmic structures, and the direct correlation between redshift and distance and age. Yet, it was also riddled with profound enigmas: the elusive nature of dark matter, the impetus behind dark energy's accelerating expansion, and the events predating inflation. It functioned, but at the cost of demanding faith in unseen, undefined, and often untestable entities. The Webb telescope has now unveiled galaxies exhibiting characteristics, age, mass, and organization that seem improbable for their observed high redshifts, contradicting the standard model's predictions. This model envisioned the early universe as a turbulent, cooling soup of particles, where the formation of galaxies with the complexity and scale observed by Webb would necessitate hundreds of millions, if not billions, of years. However, Webb's data suggests such structures coalesced within a mere 200 to 300 million years following the supposed cosmic genesis. This discrepancy is not a minor adjustment. It represents a fundamental break, potentially invalidating the model's core tenets regarding time, matter, and energy. The established temporal progression appears flawed, and the architectural frameworks it predicts are demonstrably incomplete. More unsettling is the increasing discordance among fundamental cosmological measurements. The Hubble constant, quantifying the universe's expansion rate, yields divergent values depending on whether it's derived from early universe observations, like the cosmic microwave background, or from measurements of local galaxies observed by Webb. This widening gap suggests we might not even be measuring the same fundamental reality. These challenges transcend mere observational discrepancies. They strike at the conceptual heart of the Standard Model. If galaxies form more rapidly, if time itself exhibits a different behavior, and if redshift is an unreliable chronometer, then the very foundations of lambda CDM begin to crumble, prompting serious reevaluation within the scientific community. Some researchers propose that Webb's findings necessitate an entirely new theoretical framework for the universe, one that doesn't merely patch the existing model, but is conceived anew. This could entail a departure from paradigms where dark matter and general relativity reign supreme, moving towards theories incorporating quantum information, emergent spacetime, or currently unknown physical laws. There's also a call to re-examine existing data through a fresh lens, acknowledging the possibility of flawed initial predictions. If Webb's observations consistently diverge from our expectations, it compels us to reconsider our interpretations. The cosmic microwave background, long considered the definitive portrait of the nascent universe, may be subject to misinterpretation. Perhaps dark matter is not a discrete particle but a pervasive field, or a manifestation of inexplicable forces. It's conceivable that dark energy's influence on cosmic expansion is fundamentally different from our current understanding, or that space itself possesses dynamic properties we haven't yet fathomed. This is not a rejection of scientific inquiry. Rather, it embodies the scientific spirit of confronting the unknown and refusing to avert one's gaze. The Standard Model has served us admirably, enabling explorations from lunar missions to the farthest reaches of space. However, models are tools, not absolute truths, and when they cease to align with empirical evidence, the impetus for innovation arises. The scientific community's reaction to the James Webb Space Telescope's initial images was a mixture of anticipation and trepidation. While some expected enhanced astronomical views and deeper insights, few foresaw findings that would fundamentally challenge the edifice of modern cosmology. The influx of data, revealing galaxies of improbable mass and structure forming remarkably soon after the Big Bang, and black holes appearing to coalesce far faster than predicted, elicited a spectrum of responses from scientists: astonishment, caution, and profound contemplation. Discussions within research institutions and scientific publications underscored a pivotal realization. Webb was not only illuminating the cosmos, but also exposing the limitations of our current understanding. Many cosmologists expressed a blend of awe and disbelief. For some, these anomalies were exhilarating, offering a long-awaited license to question long-held assumptions within the confines of lambda CDM. As one astrophysicist remarked, "We've been given the opportunity to rebuild cosmology from its foundations, and it would be foolish not to seize it." Conversely, others adopted a more reserved, even resistant, stance. The Standard Model's longevity and predictive success, encompassing cosmic background radiation, large-scale structures, and light element abundances, are undeniable. For these scientists, anomalies are not precursors to abandonment, but prompts for refinement. Hypotheses about more efficient early star formation, a greater role for dark matter, or variations in inflationary processes are considered plausible explanations. They foresee an evolutionary process of minor adjustments rather than a complete overhaul. Indeed, scientific progress is typically characterized by gradual, meticulous correction, with paradigm shifts emerging subtly through footnotes, conference discussions, and peer-reviewed exchanges, rather than through dramatic pronouncements. Nevertheless, an undercurrent of tension is palpable. Concerns are voiced that the cosmological community has become overly attached to established models, exhibiting an unwillingness to acknowledge when data no longer aligns. Historical precedents are cited, such as the resistance to heliocentrism, the initial dismissal of quantum theory, and the slow acceptance of plate tectonics, suggesting a potential pattern of entrenched thinking hindering progress. One theorist warns, "A model can become dogma, and dogma is the antithesis of discovery." This tension is particularly evident in public discourse, where headlines proclaiming, "James Webb could rewrite cosmic history," or "Big Bang under fire," now contrast with previous narratives praising the standard model. Astrophysicists engage in spirited debates on social media regarding redshift measurements and early galaxy formation, mirroring philosophical discussions on the nature of time. While some observers revel in the ensuing intellectual ferment, others advocate for a more measured approach. A significant portion of the ongoing debate stems from the novelty of Webb's data. We are encountering unprecedented cosmic vistas with extraordinary detail, courtesy of its advanced infrared capabilities. The question remains whether these perplexing observations represent genuine phenomena or are artifacts of our current interpretive frameworks. Possibilities of calibration errors, unforeseen observational biases, and misinterpretations persist. Nevertheless, multiple independent research teams, employing diverse methodologies and instruments, are corroborating similar findings. Early galaxies defying formation models, redshift data posing challenging questions, and black holes seemingly bypassing evolutionary stages. As these patterns solidify into established facts, a new cohort of physicists, less encumbered by historical dogma and more adept at navigating uncertainty, is emerging. For this generation, Webb's revelations are not a crisis but an invitation to explore novel concepts, revive neglected theories, and construct models that more accurately reflect a universe potentially stranger, older, or more profound than previously imagined. Consequently, unconventional ideas such as tired light, plasma cosmology, and cyclical or bouncing universes are regaining attention. Researchers are also developing quantum gravity models that circumvent singularities and conceptualize spacetime as a network of entanglement and information governed by probabilistic principles. What was once relegated to the periphery is now garnering serious consideration, not as definitive solutions, but as legitimate avenues of inquiry. Ultimately, the most honest stance acknowledges the limits of our knowledge, as science thrives not on safeguarding existing certainties, but on bravely and curiously exploring the unknown. The James Webb Telescope excels in this regard, by highlighting the discrepancies that challenge our current understanding. For the proponents of the Big Bang Theory, it represents not merely a hypothesis, but a rigorously tested framework that has withstood one of science's most demanding crucibles: prediction, observation, and repeatability. The standard model's triumph lies in its prescient prediction of the cosmic microwave background, its accurate accounting of light element abundances in the early universe, and its explanation of space expansion, large-scale structure formation, and the evolution of cosmic voids. These are not minor achievements. They are foundational pillars upon which the model's esteemed status rests. Consequently, when the James Webb Telescope reveals galaxies appearing more mature than anticipated or black holes seemingly forming prematurely, adherents of the Big Bang do not succumb to panic. Instead, they engage in meticulous analysis, adjust parameters, and probe the boundaries of existing theoretical frameworks. A common defense posits that Webb is showcasing not the average galaxy at a given redshift, but rather exceptional outliers, those that formed earlier or evolved more rapidly than the norm. Another explanation points to selection bias, suggesting that current infrared observations might preferentially detect the brightest and densest galaxies, leaving fainter, more typical examples yet to be fully catalogued. As Webb amasses more data, including less luminous galaxies, these apparent anomalies may resolve into more conventional cosmic patterns. Furthermore, the influence of intervening dust and lensing material, along with gravitational effects, could be distorting the perceived age, brightness, or organization of these galaxies. Some proponents argue that these findings may not indicate a flaw in the standard model itself, but rather an incorrect interpretation of observational data. A practical perspective also emphasizes that, despite its challenges, the standard model remains the most effective framework for studying and comprehending the universe. It does not necessitate outright abandonment, but rather evolution. This could involve incorporating new forms of dark matter, refining inflationary models, or proposing novel early-stage explosion processes. This approach mirrors how Newtonian physics, rather than being discarded, was integrated into the broader context of relativity. Loyalists also caution against anomaly hunting, the tendency to seize upon unexplained data points and construct entire alternative theoretical structures around them. Anomalies, they contend, are not unprecedented. The history of cosmology is replete with them, most of which have eventually found their place within the prevailing model as more data became available. As one cosmologist noted, science progresses not solely on excitement, but on consistency breaks across the board. That point has not yet been reached. This position is entirely justifiable. Paradigm shifts in science are infrequent and only warranted when no amount of adjustment can reconcile an established model with new observations. As of now, many of Webb's findings, while startling, have not yet crossed this critical threshold. From the perspective of Big Bang adherents, the onus of proof remains with the challengers. However, perhaps the most commendable aspect of these loyalists is not their steadfastness to the Big Bang, but their unwavering commitment to rigor. The scientific method demands skepticism, not only towards novel ideas, but also towards our own preconceptions. It is far easier to be captivated by revolutionary notions than to maintain a critical stance until the data is unequivocally sound. Yet, even these staunch supporters increasingly acknowledge the necessity for adjustments to the established paradigm. Few dispute the strangeness of Webb's discoveries, and a general consensus exists that a paradigm shift is imminent, whether it involves new insights into star formation, an altered understanding of redshift, or the initial cracks appearing in what was once considered an unbreakable theory. Therefore, the commitment is not to a specific theory, but to the scientific method itself. The Big Bang remains the default explanation because it has proven effective. However, should evidence emerge that compellingly necessitates a different narrative, even the most dedicated adherents understand their obligation to adapt. Science does not disintegrate when the foundations of a theory begin to falter. Instead, it transforms. Since the James Webb Telescope's discoveries, which appear to contradict our current cosmological understanding, a quiet but accelerating revolution is underway in theoretical physics. An increasing number of cosmologists are exploring ambitious new models that fundamentally alter our conception of the universe's origins. These models, often previously marginalized due to their divergence from established historical timelines, are now gaining prominence. Among the most frequently discussed is the Big Bounce model. Instead of a universe born from a singular explosive event, the Big Bounce proposes a cyclical existence for our cosmos, perpetually undergoing cycles of expansion, contraction, and rebound across infinite time. Within this framework, the early galaxies detected by Webb are not premature, but rather remnants of a preceding cosmic cycle. Gravity compresses the universe until it rebounds into a new phase of expansion, implying no true beginning, only continuous transformation. Roger Penrose, a Nobel laureate and a leading figure in modern physics, has proposed conformal cyclic cosmology, CCC. This model suggests that the conditions at the inception of a new universe are identical to those at the conclusion of the previous one. This occurs because expansion stretches the universe to such an extreme that all constituents break down into massless particles, with no discernible boom, as one eon transitions into the next. Webb's observation of unexpected order in the early universe could potentially be interpreted as residual information from a previous cosmic epoch. Emergent spacetime models are also garnering considerable attention. These theories posit that space and time are not fundamental properties, but rather arise from underlying quantum information structures. In these frameworks, the universe operates akin to a complex computational program, where entanglement and the flow of information give rise to phenomena such as distance, duration, and gravity. The perceived disruption in the timeline is not a flaw, but a reflection of our limited perception of time. Certain interpretations of this theory suggest that the early universe appeared fully formed because spacetime itself materialized instantaneously, analogous to initiating a video game. In more speculative domains, theories like plasma cosmology challenge the concept of universal expansion altogether. This model envisions the universe as a vast, stable structure shaped by electromagnetic forces rather than gravity and dark energy. In this context, redshift is attributed not to expansion, but to energy loss resulting from interactions within the intergalactic medium, a revival of an earlier hypothesis. Despite its controversial nature and frequent dismissal by mainstream astrophysics, plasma cosmology has experienced a resurgence of interest due to Webb's challenges to conventional expansion metrics. The holographic universe model, rooted in string theory and black hole physics, proposes that our perceived three-dimensional reality is merely a projection encoded on a two-dimensional boundary. The universe is not expanding in space, but rather progressing from a surface of quantum data. The early formation of fully developed galaxies is not an anomaly within this model, but a natural consequence of information unfolding across the holographic screen. In even more radical conceptualizations, some scientists are questioning fundamental constants of nature, exploring the possibility that constants like the speed of light or the gravitational constant may have varied over cosmic history. Such variations, however minute, could have significantly influenced the early universe's formation. In this scenario, what appear as anomalies could serve as evidence that the universe once operated under a different set of physical laws. Yet other theories propose that we inhabit a multiverse, where our specific region of reality merely reflects unique initial conditions. Phenomena that seem improbable from our vantage point might be commonplace elsewhere. Within these multiversal frameworks, early galaxies, peculiar redshift behaviors, and mature stars are interpreted as features of a localized cosmic bubble rather than failures of universal laws. While these diverse theories lack a unified structure, they share a common spirit of cosmic humility, an acknowledgement that the universe may not conform to our expectations, and that uncovering truth often requires a shift in perspective. Radical models, of course, carry inherent risks. They are frequently less elegant, more challenging to test empirically, and prone to early dismissal as purely theoretical. However, they also broaden the scope of scientific discourse, opening avenues for novel mathematical explorations, groundbreaking discoveries, and unconventional approaches to long-standing problems. What if the universe lacked a beginning? Since time immemorial, humanity has gazed at the celestial expanse, pondering its origin. Every civilization has woven narratives to explain the cosmos' genesis, from divine creation to the intricate calculations of space and time in modern science. Even within a data-driven paradigm, the universe is understood to have had a birth, a period of growth and evolution, leading to our current existence and our inherent curiosity about it. This question transcends scientific inquiry, presenting a profound philosophical upheaval. A universe without a definitive beginning challenges our most fundamental frameworks of causality, purpose, and meaning. We are, by nature, narrative creatures, our brains wired for arcs with beginnings, middles, and ends. Our personal lives, from birth to death, follow this structure. Therefore, when cosmology proposes a universe devoid of an origin, it touches upon existential concerns. Central to the Standard Model is the concept of T equals zero, the singularity, the presumed commencement of space and time. However, if Webb's discoveries suggest that structure, matter, and even mature galaxies were already in place prior to this supposed initial moment, then our notion of a starting line dissolves. This has far-reaching philosophical implications, notably by challenging the concept of the first cause, a cornerstone of philosophical and theological thought for millennia. The notion that all phenomena must have a preceding cause underpins arguments for a creator, such as Aristotle's unmoved mover and the standard cosmological argument. This causal chain is disrupted if the universe is eternal, eliminating the need for a prime mover. Such a revelation could either destabilize or liberate theological perspectives. Some traditions might resist this idea, clinging to a creation event as evidence of divine intervention, while others might embrace a more timeless, omnipresent conception of divinity, one interwoven with the eternity of existence itself. Furthermore, the question of meaning is profoundly impacted. In a universe with a discernible beginning, we can envision a direction, a purpose, or a trajectory leading from creation through increasing complexity, life, and perhaps consciousness. However, an eternal universe might imply the absence of an intended direction. We may not be the culmination of a grand design, but merely a fleeting moment within an infinite flux of cosmic fluctuations. While this prospect might initially feel unsettling, it can also be profoundly liberating. It suggests that the universe does not possess an inherent, preordained meaning. Rather, meaning is something we actively create. In an endless cosmos, our task is not to follow a pre-written script but to forge our own narrative. The scientific community's reaction to the James Webb Space Telescope's initial data has been a complex tapestry of anticipation, surprise, and intense debate. While the expectation was for improved images and deeper insights, the emerging evidence of galaxies far too mature for their cosmic age, and structures forming with unprecedented speed, has set ripples of astonishment and uncertainty through the field. This unexpected influx of information has prompted scientists to reevaluate the bedrock of modern cosmology. As early findings materialized, revealing galaxies that seemed impossibly massive and densely clustered, forming rapidly in the universe's infancy, the scientific community grappled with a mix of awe, apprehension, and profound contemplation. Discussions in research institutions and scientific journals coalesced around a critical realization. The Webb telescope was not merely extending our observational reach, but also exposing the limits of our theoretical grasp. Many cosmologists responded with a blend of wonder and skepticism. For some, the findings were invigorating, presenting a rare opportunity to question assumptions that had become almost sacrosanct within the Landesidium framework. "We have been handed the chance to rewrite cosmology from the ground up," one astrophysicist declared, "and we would be foolish not to embrace it." Others, however, adopted a more cautious, even resistant, stance. The Standard Model has earned its prominence through decades of successful predictions, elegantly explaining phenomena such as the cosmic microwave background, large-scale cosmic structures, and the abundance of light elements. For these scientists, anomalies are not grounds for abandoning the model, but rather for refining it. They propose potential explanations such as more efficient star formation in the early universe, a more significant role for dark matter, or variations in the process of inflation. Their perspective leans towards an evolutionary rather than a revolutionary transformation of the existing model. It is true that science progresses not through sudden upheavals, but through slow, methodical correction. Paradigm shifts often manifest not in sensational headlines, but in subtle shifts in footnotes, the nuances of conference presentations, and the rigorous discourse of peer-reviewed research. Nevertheless, an undeniable tension exists beneath the surface. Some researchers voice concern that the cosmological community has become too attached to its established models, exhibiting a reluctance to acknowledge when empirical data no longer aligns. They point to historical parallels, such as the resistance to heliocentrism, the initial dismissal of quantum theory, and the delayed acceptance of plate tectonics, suggesting a potential recurrence of intellectual inertia. A model can become dogma, and dogma is the enemy of discovery, warns one theorist. This strain is most palpable in public discourse, where headlines like, "James Webb could rewrite cosmic history," or "Big Bang under fire," now contrast sharply with past pronouncements praising the Standard Model. Astrophysicists engage in heated debates on social media concerning redshift measurements and early galaxy formation, mirroring the intensity of philosophical arguments about the nature of time. While some observers relish the ensuing intellectual chaos, others advocate for a more measured approach. A significant portion of the disagreement stems from the sheer novelty of Webb's data. We are witnessing unprecedented views of the universe with an unparalleled level of detail, thanks to its advanced infrared imaging capabilities. It remains uncertain whether these peculiar observations represent genuine phenomena or are the result of misinterpretation. The possibility of calibration errors, unknown observational biases, and reading mistakes still exists. However, multiple research teams employing independent methodologies and instruments are corroborating similar findings. Early galaxies that defy formation models, redshift data that raises uncomfortable questions, and black holes that appear to have circumvented evolutionary stages. As these patterns solidify into confirmed facts, a new generation of physicists is stepping forward. These researchers, less wedded to established doctrines and more comfortable navigating the unknown, view Webb's revelations not as a crisis but as an invitation to explore novel ideas, resurrect discarded theories, and construct models that more accurately reflect a universe that may be stranger, older, or more profound than we previously dared to imagine. Consequently, unconventional ideas such as tired light, plasma cosmology, and bouncing universes are regaining attention. Researchers are also developing quantum gravity models that dispense with singularities and conceptualize spacetime as a network of entanglement and information governed by probabilistic principles. What was once confined to the fringes is now receiving serious consideration, not necessarily as definitive solutions, but as legitimate avenues of inquiry. Ultimately, the most honest stance acknowledges the limits of our knowledge, as science thrives not on safeguarding existing certainties, but on bravely and curiously exploring the unknown. The James Webb Telescope is an unparalleled tool in this endeavor, adept at highlighting the discrepancies that challenge our current understanding. For the proponents of the Big Bang Theory, it represents not merely a hypothesis, but a rigorously tested framework that has withstood one of science's most demanding crucibles: prediction, observation, and repeatability. The Standard Model's triumph lies in its prescient prediction of the cosmic microwave background, its accurate accounting of light element abundances in the early universe, and its explanation of space expansion, large-scale cosmic structure formation, and the evolution of cosmic voids. These are not minor achievements. They are foundational pillars upon which the model's esteemed status rests. Consequently, when the James Webb Telescope reveals galaxies appearing more mature than anticipated or black holes seemingly forming prematurely, adherents of the Big Bang do not succumb to panic. Instead, they engage in meticulous analysis, adjust parameters, and probe the boundaries of existing theoretical frameworks. A common defense posits that Webb is showcasing not the average galaxy at a given redshift, but rather exceptional outliers, those that formed earlier or evolved more rapidly than the norm. Another explanation points to selection bias, suggesting that current infrared observations might preferentially detect the brightest and densest galaxies, leaving fainter, more typical examples yet to be fully catalogued. As Webb amasses more data, including less luminous galaxies, these apparent anomalies may resolve into more conventional cosmic patterns. Furthermore, the influence of intervening dust and lensing material, along with gravitational effects, could be distorting the perceived age, brightness, or organization of these galaxies. Some proponents argue that these findings may not indicate a flaw in the standard model itself, but rather an incorrect interpretation of observational data. A practical perspective also emphasizes that, despite its challenges, the standard model remains the most effective framework for studying and comprehending the universe. It does not necessitate outright abandonment, but rather evolution. This could involve incorporating new forms of dark matter, refining inflationary models, or proposing novel early-stage explosion processes. This approach mirrors how Newtonian physics, rather than being discarded, was integrated into the broader context of relativity. Loyalists also caution against anomaly hunting, the tendency to seize upon unexplained data points and construct entire alternative theoretical structures around them. Anomalies, they contend, are not unprecedented. The history of cosmology is replete with them, most of which have eventually found their place within the prevailing model as more data became available. As one cosmologist noted, science progresses not solely on excitement, but on consistency breaks across the board. That point has not yet been reached. This position is entirely justifiable. Paradigm shifts in science are infrequent and only warranted when no amount of adjustment can reconcile an established model with new observations. As of now, many of Webb's findings, while startling, have not yet crossed this critical threshold. From the perspective of Big Bang adherents, the onus of proof remains with the challengers. However, perhaps the most commendable aspect of these loyalists is not their steadfastness to the Big Bang, but their unwavering commitment to rigor. The scientific method demands skepticism, not only towards novel ideas, but also towards our own preconceptions. It is far easier to be captivated by revolutionary notions than to maintain a critical stance until the data is unequivocally sound. Yet, even these staunch supporters increasingly acknowledge the necessity for adjustments to the established paradigm. Few dispute the strangeness of Webb's discoveries, and a general consensus exists that a paradigm shift is imminent, whether it involves new insights into star formation, an altered understanding of redshift, or the initial cracks appearing in what was once considered an unbreakable theory. Therefore, the commitment is not to a specific theory, but to the scientific method itself. The Big Bang remains the default explanation because it has proven effective. However, should evidence emerge that compellingly necessitates a different narrative, even the most dedicated adherents understand their obligation to adapt. Science does not disintegrate when the foundations of a theory begin to falter. Instead, it transforms. Since the James Webb Telescope's discoveries, which appear to contradict our current cosmological understanding, a quiet but accelerating revolution is underway in theoretical physics. An increasing number of cosmologists are exploring ambitious new models that fundamentally alter our conception of the universe's origins. These models, often previously marginalized due to their divergence from established historical timelines, are now gaining prominence. Among the most frequently discussed is the Big Bounce model. Instead of a universe born from a singular explosive event, the Big Bounce proposes a cyclical existence for our cosmos, perpetually undergoing cycles of expansion, contraction, and rebound across infinite time. Within this framework, the early galaxies detected by Webb are not premature, but rather remnants of a preceding cosmic cycle. Gravity compresses the universe until it rebounds into a new phase of expansion, implying no true beginning, only continuous transformation. Roger Penrose, a Nobel laureate and a leading figure in modern physics, has proposed conformal cyclic cosmology, CCC. This model suggests that the conditions at the inception of a new universe are identical to those at the conclusion of the previous one. This occurs because expansion stretches the universe to such an extreme that all constituents break down into massless particles, with no discernible boom, as one eon transitions into the next. Webb's observation of unexpected order in the early universe could potentially be interpreted as residual information from a previous cosmic epoch. Emergent spacetime models are also garnering considerable attention. These theories posit that space and time are not fundamental properties, but rather arise from underlying quantum information structures. In these frameworks, the universe operates akin to a complex computational program, where entanglement and the flow of information give rise to phenomena such as distance, duration, and gravity. The perceived disruption in the timeline is not a flaw, but a reflection of our limited perception of time. Certain interpretations of this theory suggest that the early universe appeared fully formed because spacetime itself materialized instantaneously, analogous to initiating a video game. In more speculative domains, theories like plasma cosmology challenge the concept of universal expansion altogether. This model envisions the universe as a vast, stable structure shaped by electromagnetic forces rather than gravity and dark energy. In this context, redshift is attributed not to expansion, but to energy loss resulting from interactions within the intergalactic medium, a revival of an earlier hypothesis. Despite its controversial nature and frequent dismissal by mainstream astrophysics, plasma cosmology has experienced a resurgence of interest due to Webb's challenges to conventional expansion metrics. The holographic universe model, rooted in string theory and black hole physics, proposes that our perceived three-dimensional reality is merely a projection encoded on a two-dimensional boundary. The universe is not expanding in space, but rather progressing from a surface of quantum data. The early formation of fully developed galaxies is not an anomaly within this model, but a natural consequence of information unfolding across the holographic screen. In even more radical conceptualizations, some scientists are questioning fundamental constants of nature, exploring the possibility that constants like the speed of light or the gravitational constant may have varied over cosmic history. Such variations, however minute, could have significantly influenced the early universe's formation. In this scenario, what appear as anomalies could serve as evidence that the universe once operated under a different set of physical laws. Yet other theories propose that we inhabit a multiverse, where our specific region of reality merely reflects unique initial conditions. Phenomena that seem improbable from our vantage point might be commonplace elsewhere. Within these multiversal frameworks, early galaxies, peculiar redshift behaviors, and mature stars are interpreted as features of a localized cosmic bubble rather than failures of universal laws. While these diverse theories lack a unified structure, they share a common spirit of cosmic humility, an acknowledgement that the universe may not conform to our expectations, and that uncovering truth often requires a shift in perspective. Radical models, of course, carry inherent risks. They are frequently less elegant, more challenging to test empirically, and prone to early dismissal as purely theoretical. However, they also broaden the scope of scientific discourse, opening avenues for novel mathematical explorations, groundbreaking discoveries, and unconventional approaches to long-standing problems. What if the universe lacked a beginning? Since time immemorial, humanity has gazed at the celestial expanse, pondering its origin. Every civilization has woven narratives to explain the cosmos' genesis, from divine creation to the intricate calculations of space and time in modern science. Even within a data-driven paradigm, the universe is understood to have had a birth, a period of growth and evolution, leading to our current existence and our inherent curiosity about it. This question transcends scientific inquiry, presenting a profound philosophical upheaval. A universe without a definitive beginning challenges our most fundamental frameworks of causality, purpose, and meaning. We are, by nature, narrative creatures, our brains wired for arcs with beginnings, middles, and ends. Our personal lives, from birth to death, follow this structure. Therefore, when cosmology proposes a universe devoid of an origin, it touches upon existential concerns. Central to the standard model is the concept of T=0, the singularity, the presumed commencement of space and time. However, if Webb's discoveries suggest that structure, matter, and even mature galaxies were already in place prior to this supposed initial moment, then our notion of a starting line dissolves. This has far-reaching philosophical implications, notably by challenging the concept of the first cause, a cornerstone of philosophical and theological thought for millennia. The notion that all phenomena must have a preceding cause underpins arguments for a creator, such as Aristotle's unmoved mover and the standard cosmological argument. This causal chain is disrupted if the universe is eternal, eliminating the need for a prime mover. Such a revelation could either destabilize or liberate theological perspectives. Some traditions might resist this idea, clinging to a creation event as evidence of divine intervention, while others might embrace a more timeless, omnipresent conception of divinity, one interwoven with the eternity of existence itself. Furthermore, the question of meaning is profoundly impacted. In a universe with a discernible beginning, we can envision a direction, a purpose, or a trajectory leading from creation through increasing complexity, life, and perhaps consciousness. However, an eternal universe might imply the absence of an intended direction. We may not be the culmination of a grand design, but merely a fleeting moment within an infinite flux of cosmic fluctuations. While this prospect might initially feel unsettling, it can also be profoundly liberating. It suggests that the universe does not possess an inherent, preordained meaning. Rather, meaning is something we actively create. In an endless cosmos, our task is not to follow a pre-written script but to forge our own narrative. Our task is to imbue our existence with self-created significance, a defiant act against the universe's perceived indifference. We also grapple with the concept of time itself. Philosophers like Immanuel Kant posited that time isn't an external reality, but a construct of our minds. If the cosmos lacks a definitive origin, then time's importance might be diminished. Some contemporary scientists suggest time is an emergent property, arising from interconnected quantum systems or thermodynamic patterns. From this perspective, any perceived beginning isn't a concrete event but a boundary of our comprehension. This leads to a potentially unsettling realization. Our fundamental questions might be misdirected. If the universe has always existed, then inquiring about its commencement is akin to asking what lies north of the North Pole, a nonsensical endeavor, misusing language and logic. Perhaps our innate drive to understand our origins is merely a consequence of our temporal existence, not a reflection of the universe's true structure. This isn't to suggest chaos, but rather a profound, underlying order. The James Webb Space Telescope transcends its function as mere optics. It serves as a mirror reflecting both the nascent light of the cosmos and the inherent limitations of human understanding. It reveals that even our most cherished concepts, like beginnings, causality, and narrative arcs, might be comforting illusions. The quest for knowledge doesn't end with the James Webb. Subsequent generations of ambitious projects will delve even deeper, wider, and into more peculiar territories. This marks the dawn of a new scientific epoch. Many eagerly anticipate NASA's Nancy Grace Roman Space Telescope, slated for deployment later this decade. Reports suggest Roman will boast a field of view 100 times larger than Hubble's, retaining similar sharpness, making it ideal for meticulously surveying vast celestial expanses. While Webb scrutinizes the distant past with intense, narrow focus, Roman will chart the universe's large-scale architecture, observing galaxy clustering and the impact of dark energy on cosmic expansion. Where Webb highlights cosmic peculiarities, Roman will quantify their strangeness, discerning whether they are random occurrences or systemic flaws in our conceptual framework. On Earth, the Vera C. Rubin Observatory in Chile, nearing full operational status, will undertake the Legacy Survey of Space and Time (LSST). This ambitious decade-long initiative aims to catalog billions of galaxies, track transient phenomena like supernovae and asteroids, and generate a dynamic visual chronicle of the universe. Rubin's strength lies not in depth, but in observing motion and patterns, providing time-dependent insights that complement Webb's static snapshots. Should the early universe have been more volatile, rapidly evolving, or discontinuous than currently understood, Rubin will be instrumental in capturing those subtle temporal imprints. Meanwhile, Europe's Euclid mission, launched by ESA, is already meticulously scanning immense cosmic regions to unravel the mysteries of dark energy and dark matter. Although it may not match Webb's infrared prowess, Euclid complements Webb by investigating gravitational lensing, the phenomenon of light from distant galaxies being distorted by massive cosmic structures. This will enable scientists to test the validity of general relativity at cosmic scales, potentially paving the way for more unconventional theories. The Extremely Large Telescope, ELT, a colossal instrument under construction in Chile's Atacama Desert, features a 39-meter mirror, the largest of its kind, empowering it to directly observe the universe's first stars and exoplanets. This capability will unlock unprecedented spectroscopic analysis of ancient galaxies. Unlike space-based observatories, its ground-based nature allows for upgrades and modifications, establishing it as a long-term sentinel for detecting quantum and chemical signatures of cosmic entities that defy current models. Looking further ahead, NASA is conceptualizing the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, an ambitious project envisioned to surpass Webb's capabilities significantly. LUVOIR is designed to investigate everything from the origins of life on exoplanets to enigmatic celestial objects hidden in plain sight. If realized, LUVOIR would represent the most powerful all-purpose space telescope ever conceived, potentially offering definitive answers regarding the universe's very inception. Beyond LUVOIR, even more speculative concepts are in development. Missions like LISA, Laser Interferometer Space Antenna, aim to detect gravitational waves emanating from space, opening a novel sensory channel for comprehending black hole mergers and the universe's fundamental vibrational frequencies. Gravitational waves offer insights unobtainable through light, and may reveal echoes from events predating light's ability to propagate. As the lines between astrophysics, quantum theory, and cosmology continue to blur, future observational tools might diverge from traditional telescope designs. They could manifest as satellite constellations forming artificial interferometers, or employ quantum sensors to detect minute spacetime curvature shifts. Alternatively, they might focus on studying neutrino backgrounds or residual gravitational radiation from hypothetical pre-Big Bang states. The media often sensationalizes scientific findings, sometimes misrepresenting them. Claims of the Big Bang's demise, for instance, are frequently overstated. While nuance is vital for scientific progress, the Internet thrives on controversy and clickable content. The James Webb Telescope has indeed produced perplexing data, revealing galaxies that appear disproportionately large, ancient, and structured for their observed redshift. These findings stimulate valuable reevaluation of our cosmological theories, but do not invalidate the Big Bang, much like early aviation accidents didn't extinguish the concept of flight. Many experts quoted in popular articles have been misrepresented, their statements taken out of context, or their significance exaggerated. For seasoned cosmologists, pronouncements like, "The universe is older than we thought," or "The Big Bang is in crisis," require cautious interpretation. The Big Bang is not a singular event, but a model grounded in a robust framework of empirical evidence, including the expansion of space, the cosmic microwave background radiation, and the abundance of light elements. These foundational observations remain intact. James Webb has not disproven them. Instead, it has reignited discussions about the immediate aftermath and the formation of primordial structures. However, in media narratives, subtle challenges to early universe structure formation have rapidly morphed into definitive declarations of the Big Bang's obsolescence. This pattern is a recurring issue in science communication. Isolated anomalies are presented as proof of established knowledge being fundamentally flawed, and cautious scientific commentary is transformed into clickbait headlines. The scientific method, characterized by gradual refinement, peer review, and measured interpretation, is often supplanted by spectacle. This disconnect carries tangible consequences, fostering public misunderstanding, polarizing discourse, and eroding trust. For casual news consumers, the constant pendulum swing between science proving everything and science being entirely wrong creates the illusion that scientific inquiry is mere guesswork, fragile, and subject to constant revision with each new image. In reality, science is inherently resilient. Theories are not dogma, but pragmatic tools. When tools prove inadequate, they are refined, adapted, or replaced. The James Webb Telescope fulfills its purpose by challenging complacency, exposing blind spots, and sharpening inquiry. It's crucial to recognize that many scientists welcome these anomalies not to abandon the Big Bang, but because they present novel avenues for exploration. For years, cosmology had become somewhat stagnant. The standard model adequately explained most phenomena. However, Webb has reopened the celestial vault, hinting at deeper, undiscovered layers. The public deserves more than oversimplified narratives of the Big Bang's demise or survival. They deserve to understand that this is not a conflict but an ongoing dialogue, albeit one characterized by disagreement, rigor, collaboration, and humility. The scientific community is not divided into factions of heroes and villains, but comprises individuals dedicated to understanding a reality far grander than any single person can grasp. Some scientists actively support the standard model, others propose radical alternatives, and many more are investigating potential data limitations, such as the influence of dust, lensing, or redshift interpretation inaccuracies. All are united by a shared foundation of curiosity and evidence. Are we witnessing the dawn of a new era in cosmology, comparable to the mid-20th century when the cosmic microwave background was discovered and Hubble's observations revealed an expanding universe? That period, which saw the Big Bang model triumph over the steady-state theory, was a time of immense discovery, where the focus shifted from mere amazement to active investigation. This current era's golden status is not solely attributable to technological advancements, although they are significant. It stems from a renewed willingness to reimagine established paradigms. For decades, the standard model of cosmology served as a secure intellectual haven. Now, scientists are embracing the winds of uncertainty, revisiting dormant theories, and proposing novel models where information, rather than matter, is the fundamental constituent. They are questioning whether galaxies formed prior to the timescales permitted by current physics, and are pursuing anomalies rather than dismissing them. New instruments, like the Nancy Grace Roman Space Telescope, the Vera C. Rubin Observatory, and the Euclid Probe, are poised to collect unprecedented volumes of data. These instruments will map billions of galaxies, track cosmic acceleration, and probe dark energy in ways that will either solidify or redefine our understanding. This endeavor is no longer a solitary pursuit, but a coordinated fleet of exploration. Concurrently, ground-based facilities, like the extremely large telescope, alongside theoretical advancements in quantum gravity and emergent spacetime, are broadening our perspective from both observational and conceptual frontiers. These combined efforts form a cohesive network of insight, where each discovery cross-validates, challenges, or reframes the others, creating an exponential feedback loop of discovery. However, scientific advancement is not the sole reason for this era's distinction. Collaboration across disciplines, national borders, and even diverse philosophical frameworks is paramount. Philosophers are regaining prominence in scientific discourse. Mathematicians are developing new cosmological theories. Artificial intelligence and machine learning are accelerating pattern recognition in cosmic data, and amateur scientists are identifying supernovae and exoplanets using previously unimaginable tools. This moment feels distinct because it is driven not by established facts, but by boundless possibility. The questions being posed transcend mere models, mathematics, or even observational instruments. Many ponder fundamental truths, our purpose, our place in the cosmos, and the potential uniqueness of our world. Faith is absent, only a growing sense of inquiry prevails. Perhaps the true hallmark of a golden age is not possessing answers, but cultivating the capacity to ask more profound questions, questions that would have been unthinkable a generation prior. Consider the implications. Our most fundamental assumptions about the universe are currently being rigorously tested, not by narratives, but by empirical evidence. Each new image presents an opportunity to reevaluate our cosmic significance. When scientists adeptly defend established principles while simultaneously acknowledging their limitations, a theory concludes, and wonder commences. The Big Bang Theory has served as our guiding principle for nearly a century, providing a framework for understanding our cosmic origins and place. It illuminated our path forward, from Einstein's equations and Hubble's red shift to microwave background maps and particle accelerators, fostering grander thinking and conceptualizing time as a thread and space as a fabric. This could herald something far more robust, as failure is not the cessation of an idea, but the return of all. It is the realization that the map no longer corresponds to the terrain, and rather than fear, we embrace the potential of the unknown. This kind of potential emerges when we relinquish outdated tools in pursuit of new ones. We are presently in such a transformative period. We are confronting the possibility that space may not be what we perceive, that time may not flow uniformly, that the early universe may have bypassed developmental stages dictated by our current physics, and that galaxies formed prematurely with oversized black holes at their cores. In the past, such anomalies would have sparked hushed discussions within academic circles. Today, these revelations resonate globally through digital platforms, classrooms, podcasts, and social media. The investigation is no longer confined to laboratories. It is a collective undertaking. It is not about possessing all the answers, but about standing at the precipice of our knowledge and acknowledging, perhaps we were mistaken. Space might not be what we assumed. What we consider a beginning might not be one at all. We may require a new conceptual language, woven from quantum threads, emergent rules, or phenomena yet undiscovered. The James Webb Space Telescope is more than a collection of instruments. It is a reflective surface for our consciousness, revealing the universe not as we wish it to be, but as it truly is, complex, magnificent, and unfinished. Those of us who contemplate, question, dream, and inquire must engage with this revelation. The next phase may not immediately yield new ideas. It could involve uncertainty, confusion, debate, protracted periods of false starts, and discarded models. Yet, every golden age originates from disruption, from the perceived dissolution of solid ground, from which new structures are built. The James Webb Space Telescope has not only provided us with stunning imagery, but has also exposed a gap in our oldest cosmological narrative. Whether the Big Bang Theory ultimately collapses or evolves, one certainty remains. We stand on the cusp of a new cosmic era, where inquiry drives discovery and mystery yields to understanding. If this exploration has reshaped your perspective on the universe, continue this journey. Like, share, and subscribe to join us as we delve deeper into the questions that underpin existence. For both the universe and ourselves are in a constant state of transformation.